Subscribe to the channel so you don't miss out on any of these videos. Imagine a vast, cosmic dance playing out over billions of years, an intricate choreography of colossal forces shaping the very structure of the universe itself. Picture galaxies, those sprawling islands of stars, gas, and dark matter, engaging in a slow but dramatic tug-of-war, their fates intertwined by gravity. Sometimes they pass each other with just a fleeting glance, like strangers on a crowded street. Other times, they lock together in an embrace so profound it changes their shapes, their paths, and even their identities forever. These interactions, known as galactic tides, hold the secrets to how galaxies evolve and interact, and their consequences ripple across millions of light years. What drives this silent but monumental cosmic drama? And how does it affect not just galaxies themselves, but the universe at large? Let's unravel these mysteries together. Galactic tides are the gravitational effects that occur when galaxies interact with one another. While the term might bring to mind the rhythmic rise and fall of Earth's ocean tides, the forces at play here are of an entirely different magnitude. When two galaxies approach each other, their immense gravitational fields stretch and distort each other, creating dramatic structures like tidal tails, bridges, and, in some cases, complete mergers. These encounters are not mere accidents. They are governed by the fundamental force of gravity, which acts as both the architect and the destroyer in the universe. At the heart of galactic tides lies the concept of gravitational interaction. Every galaxy, no matter how distant or isolated it may seem, exerts a gravitational pull on its neighbors. This pull becomes especially significant when galaxies come close to one another, their gravity competing for dominance. The larger and more massive a galaxy, the stronger its influence. Smaller galaxies, such as dwarf galaxies, often bear the brunt of these interactions, their shapes stretched and distorted as they are pulled toward their larger companions. One of the most fascinating consequences of galactic tides is the formation of tidal tails. These are long, thin streams of stars and gas that extend outward from a galaxy, often stretching for hundreds of thousands of light years. They form when the gravitational pull of a nearby galaxy rips material away, flinging it into space. Tidal tails are like the cosmic fingerprints of an encounter, providing clues about the galaxy's masses, speeds, and trajectories. For instance, the Antennae galaxies, located about 45 million light-years away, showcase some of the most dramatic tidal tails ever observed, a vivid testament to the forces at play during their merger. But tidal tails are just one part of the story. Galactic bridges are another hallmark of these interactions. These structures form when streams of gas and stars are pulled between two galaxies, creating a physical connection that looks almost like a bridge. Such bridges often act as pathways for material to flow from one galaxy to another, fueling bursts of star formation in the process. This exchange of material can profoundly alter the chemical composition and star-making potential of the galaxies involved, effectively reshaping their futures. Perhaps the most transformative outcome of galactic tides is the phenomenon of galaxy mergers. When two galaxies collide, their stars, gas, and dark matter interact in complex ways, often resulting in the formation of a single, larger galaxy. These mergers are not instantaneous. They unfold over hundreds of millions to billions of years, with the galaxies passing through each other multiple times before finally settling into a stable configuration. The result is often an entirely new type of galaxy, such as an elliptical galaxy, which is thought to form from the merger of two spiral galaxies. The effects of galactic mergers extend far beyond the galaxies themselves. When galaxies collide, their central supermassive black holes are also drawn together, eventually merging to form an even larger black hole. This process can release tremendous amounts of energy in the form of gravitational waves, ripples in spacetime that propagate across the universe. Observing these waves provides scientists with a unique window into the dynamics of galactic interactions and the behavior of black holes. Galactic tides also play a crucial role in the evolution of galaxy clusters, which are groups of galaxies bound together by gravity. Within these clusters, galaxies interact frequently, exchanging material and reshaping each other over time. These interactions can strip away a galaxy's outer layers, leaving behind a smaller, more compact core. They can also trigger bursts of star formation or, conversely, quench star formation entirely by removing the gas needed to create new stars. One of the most intriguing aspects of galactic tides is their role in the large-scale structure of the universe. When viewed on a cosmic scale, galaxies are not randomly distributed. They form a web-like pattern of clusters, filaments, and voids. Galactic interactions contribute to this structure by redistributing matter and energy, influencing the growth and distribution of galaxies over billions of years. Understanding these processes is key to unraveling the history and future of the universe itself. The study of galactic tides is not just a theoretical endeavor. It is grounded in observations made possible by powerful telescopes and advanced simulations. For example, the Hubble Space Telescope has captured stunning images of interacting galaxies, revealing the intricate details of tidal tails, bridges, and mergers. Meanwhile, computer simulations allow scientists to model these interactions, testing hypotheses and exploring scenarios that are impossible to observe directly. These tools have revolutionized our understanding of how galaxies evolve, providing insights into everything from star formation to the behavior of dark matter. Despite these advances, many questions remain unanswered. For instance, how do galactic interactions influence the formation of supermassive black holes? What role do dark matter and dark energy play in shaping these interactions? And how do galactic tides affect the overall evolution of the universe? These mysteries drive ongoing research, pushing the boundaries of what we know about the cosmos. To truly appreciate the significance of galactic tides, one must consider the scale of the events involved. These interactions unfold over timescales that dwarf human history, yet their effects are monumental, shaping the galaxies that illuminate our night sky. They remind us that the universe is a dynamic, ever-changing place, governed by forces that operate on scales both immense and minute. The story of galactic tides is a story of connection, of galaxies linked by invisible threads of gravity, their fates intertwined in a cosmic dance that spans billions of years. It is a story that challenges our understanding of the universe and our place within it, inviting us to look beyond our own world and explore the intricate, beautiful, and often mysterious workings of the cosmos. And as we continue to study these interactions, we inch closer to answering some of the biggest questions about the universe, uncovering the secrets of its past and glimpsing its future. The interplay of galactic tides also brings us to the fascinating phenomenon of starburst galaxies. These are galaxies experiencing an exceptionally high rate of star formation, often triggered by interactions or collisions with other galaxies. When galaxies collide or pass close enough to gravitationally disrupt each other, the turbulence can compress vast clouds of gas, igniting intense bursts of star formation. This process can create thousands of new stars in a relatively short period, altering the galaxy's characteristics for millions of years. Starburst galaxies are not just visually striking, they also serve as laboratories for understanding how galaxies evolve and create new stars. The immense amount of energy released during these starbursts illuminates regions of the universe that might otherwise remain dark, helping astronomers probe deeper into space. But starbursts are fleeting events on a cosmic timescale. Once the gas supply is depleted, the galaxy's star formation slows, leaving behind clusters of young, hot stars and changing the galaxy's appearance forever. Another fascinating aspect of galactic tides lies in their ability to strip material from galaxies, leading to a process called ram pressure stripping. When galaxies move through dense environments, such as galaxy clusters, the pressure of the intergalactic medium, an extremely thin, hot gas that fills the space between galaxies, can strip away their outer layers of gas and stars. This phenomenon can leave galaxies looking barren, with little or no material left to form new stars. It can also contribute to the enrichment of the intergalactic medium itself, as the stripped material is ejected into the surrounding space, adding heavy elements forged in stars. Galactic interactions are also deeply intertwined with the mysterious force known as dark matter. While dark matter is invisible and does not emit or absorb light, its gravitational effects are undeniable. It forms the scaffolding around which galaxies and galaxy clusters are built, and it plays a crucial role in their interactions. During galactic collisions, dark matter halos surrounding galaxies interact, influencing the dynamics of the encounter. These interactions help astronomers map the distribution of dark matter, providing insights into one of the universe's most elusive substances. One of the most spectacular examples of galactic interactions involving dark matter is the bullet cluster. This pair of colliding galaxy clusters showcases how dark matter behaves during massive cosmic collisions. Observations reveal that the dark matter in these clusters does not interact in the same way as normal matter, instead passing through the collision relatively unimpeded. This discrepancy offers critical evidence for the existence and properties of dark matter, challenging scientists to refine their theories. The study of galactic tides is further enriched by our understanding of gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity. When supermassive black holes at the centers of merging galaxies eventually collide, they produce gravitational waves detectable by instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO. These waves carry information about the masses, spins, and orbits of the black holes, offering a new way to study the dynamics of galactic interactions. The detection of such waves represents a groundbreaking step in our ability to observe the universe, allowing us to listen to cosmic events that were previously invisible. Beyond individual events, galactic tides have a profound impact on the cosmic web, the large-scale structure of the universe. As galaxies interact and merge, they contribute to the growth of galaxy clusters and filaments, the vast networks of matter that define the universe's structure. These interactions redistribute material, influencing the rate of star formation, the growth of black holes, and the evolution of galaxies within these structures. By studying the cosmic web, astronomers can trace the history of the universe, piecing together how it has changed over billions of years. The tools used to study galactic tides have advanced dramatically in recent decades. High-powered telescopes like the James Webb Space Telescope and advanced simulations on supercomputers allow researchers to observe and model galactic interactions with unprecedented detail. These technologies enable scientists to simulate the effects of gravity, dark matter, and gas dynamics on galaxies, revealing how they morph and evolve over time. These simulations often recreate phenomena like tidal tails and galaxy mergers, validating theories and providing new insights into the processes driving galactic evolution. Despite these advancements, the universe still holds many unanswered questions about galactic tides. For instance, how do repeated interactions between galaxies affect their long-term evolution? What role do magnetic fields play in shaping these interactions? And how do tidal forces influence the formation and distribution of planets within galaxies? These mysteries fuel ongoing research, inspiring new experiments and observations aimed at unlocking the secrets of the cosmos. One particularly exciting avenue of study is the role of galactic interactions in the formation of planetary systems. The material ejected during tidal interactions, including gas and dust, can serve as the building blocks for new stars and planets. By studying these processes, scientists hope to understand how planetary systems like our own form and evolve within the chaotic environments of interacting galaxies. This research has profound implications for the search for extraterrestrial life, as it sheds light on the conditions that might support habitable worlds. The implications of galactic tides extend even further, touching on fundamental questions about the nature of the universe. By studying how galaxies interact and evolve, scientists gain insights into the forces that govern the cosmos, from gravity and dark matter to the mysterious dark energy driving the universe's expansion. These discoveries not only deepen our understanding of the universe but also challenge us to rethink our place within it. As we explore these cosmic interactions, we are reminded of the interconnectedness of the universe. The same gravitational forces that shape galaxies also govern the orbits of planets, the tides on Earth, and even the formation of stars. Galactic tides are a testament to the unity of the cosmos, a reminder that every structure, from the smallest atom to the largest galaxy cluster, is part of a vast and intricate web of interactions. The story of galactic tides is far from over. With each new discovery, we uncover more about the forces shaping the universe, drawing us closer to understanding the cosmic dance that has been playing out for billions of years. And as we continue to probe the mysteries of galactic tides, we embark on a journey not just to explore the universe, but to understand the fundamental nature of existence itself. The beauty of galactic tides lies in their role as both creators and destroyers. On one hand, they lead to the creation of stunning tidal tails, intricate bridges, and new star-forming regions. On the other, they disrupt galaxies, stripping them of gas and stars, sometimes leaving them as barren remnants of their former selves. These dual effects reveal the delicate balance of forces at play in the cosmos, a balance that has shaped the universe we see today. Consider the Milky Way, our galactic home. It has its own history of interactions, both past and ongoing. The Milky Way is in the process of merging with the Sagittarius dwarf galaxy, a small satellite galaxy that has been repeatedly disrupted by our galaxy's gravitational pull. Over time, streams of stars from Sagittarius have been torn away, forming what are known as tidal streams that wrap around the Milky Way. These streams not only provide a visual testament to the power of galactic tides but also offer astronomers clues about the Milky Way's mass and structure. Even more dramatic is the Milky Way's future collision with the Andromeda Galaxy, predicted to occur in about 4.5 billion years. This monumental event will be a slow-motion dance, lasting billions of years as the two galaxies spiral toward each other, interact, and eventually merge. The collision will generate immense tidal forces, reshaping both galaxies. Stars will be flung into vast arcs, gas will be compressed to form new stars, and eventually, the two galaxies will settle into a single, larger elliptical galaxy. While this process might sound catastrophic, the vast distances between stars mean that direct collisions between them will be rare. However, the gravitational interactions will dramatically alter the structure of both galaxies, creating a new cosmic masterpiece. The study of such events has profound implications for understanding the life cycles of galaxies. Interactions like the Milky Way-Andromeda collision are not rare. They are a natural part of the cosmic evolution. Most galaxies we observe today, including our own, are the products of past mergers and interactions. These processes are not just destructive, they are also creative, driving the formation of new stars, enriching galaxies with heavy elements, and shaping the large-scale structure of the universe. One of the most remarkable aspects of galactic interactions is their ability to create new types of galaxies. For instance, elliptical galaxies are often thought to result from the merger of two or more spiral galaxies. During such mergers, the chaotic gravitational forces disrupt the ordered rotation of stars in the spiral arms, transforming the galaxy into a more spherical, or ellipsoidal shape. At the same time, the intense star formation triggered by the merger consumes much of the available gas, leaving the resulting galaxy with little material for future star formation. These processes explain why elliptical galaxies tend to have older stellar populations and appear redder than their spiral counterparts. Beyond shaping individual galaxies, galactic tides also play a role in the dynamics of galaxy clusters. Galaxy clusters are some of the largest structures in the universe, containing hundreds or even thousands of galaxies bound together by gravity. Within these clusters, galaxies are constantly interacting, their motions influenced by the cluster's gravitational field. These interactions can strip galaxies of their gas, quench star formation, and alter their shapes, contributing to the diversity of galaxy types we observe. The interplay of galactic tides and galaxy clusters also sheds light on the mysterious phenomenon of gravitational lensing. When light from a distant galaxy or quasar passes through a massive galaxy cluster, the cluster's gravitational field can bend the light, creating distorted, magnified, or even multiple images of the background object. These lensing effects not only provide stunning visuals but also allow astronomers to map the distribution of mass within galaxy clusters, including the dark matter that makes up most of their mass. By studying these lensing effects, scientists can probe the nature of dark matter and its role in the universe's structure. The complexity of galactic tides is further highlighted by their connection to supermassive black holes. Nearly every large galaxy contains a supermassive black hole at its center, with masses ranging from millions to billions of times that of the Sun. These black holes play a crucial role in galactic evolution, influencing the distribution of gas, stars, and even dark matter. During galactic mergers, the supermassive black holes from each galaxy are drawn toward each other, eventually forming a binary system. Over time, these black holes will spiral inward, releasing gravitational waves as they merge. This process not only affects the structure of the resulting galaxy but also provides a unique way to study the dynamics of black holes and their environments. Galactic tides also influence the formation of satellite galaxies, smaller companions that orbit larger galaxies. These satellites often experience tidal forces that strip them of stars and gas, creating streams of material that orbit the host galaxy. These streams are not just visually striking, they also serve as fossil records of past interactions, offering insights into the history of the host galaxy and its satellites. By studying these streams, astronomers can reconstruct the formation and evolution of galaxies like the Milky Way, piecing together a detailed picture of their past. Despite the wealth of knowledge we have gained about galactic tides, many questions remain unanswered. For example, how do these interactions influence the growth of supermassive black holes? What role do magnetic fields play in shaping the structures created by galactic tides? And how do these processes vary across different types of galaxies and environments? These questions drive ongoing research, pushing the boundaries of our understanding and inspiring new observations and simulations. As we continue to explore the mysteries of galactic tides, we are reminded of the interconnectedness of the universe. The same forces that shape galaxies also govern the orbits of stars, the formation of planets, and the structure of the cosmic web. By studying these interactions, we gain not only a deeper understanding of the universe but also a greater appreciation for the intricate dance of forces that has shaped it over billions of years. The story of galactic tides is one of creation and destruction, of beauty and chaos. It is a story that spans the entire history of the universe, from the formation of the first galaxies to the complex structures we see today. And as we continue to unravel this story, we find ourselves drawn ever closer to the ultimate questions about the nature of the cosmos and our place within it. The effects of galactic tides extend far beyond what we can observe visually. These gravitational interactions play a critical role in redistributing matter and energy on scales that shape the evolution of galaxies over billions of years. They are responsible for creating some of the most iconic features in the universe, like tidal tails and bridges, while also revealing secrets about the underlying mechanisms of cosmic evolution. Take tidal tails, for instance. These elongated streams of stars and gas, often stretching thousands of light years, are formed when two galaxies pass close enough for their gravitational forces to draw material away from each other. These tails are not random. They contain clues about the properties of the interacting galaxies, including their masses, velocities, and even the distribution of their dark matter. In fact, tidal tails are often used by astronomers as natural laboratories to study the elusive properties of dark matter. By analyzing the movement of stars within these tails, researchers can infer the gravitational influence of dark matter, which is otherwise invisible. Another fascinating structure created by galactic tides is the tidal bridge. Unlike tidal tails, which extend outward, tidal bridges form between two galaxies, connecting them with a stream of stars and gas. These bridges are temporary structures, often lasting only a few 100 million years before dissipating or merging into the interacting galaxies. They serve as a channel for the exchange of material between galaxies, a process that can trigger bursts of star formation or alter the chemical composition of the galaxies involved. Such bridges provide compelling evidence of the dynamic nature of galaxies, showing that they are not isolated entities but part of a vast and interconnected cosmic web. The process of galaxy mergers, one of the most dramatic outcomes of galactic tides, deserves special attention. When two galaxies collide, the gravitational forces at play are so immense that they can completely reshape both galaxies. Spiral galaxies, with their delicate arms and central bulges, can be transformed into irregular or elliptical galaxies. During the merger, gas clouds within the galaxies are compressed, leading to intense bursts of star formation, often referred to as starburst events. These bursts can produce hundreds or even thousands of new stars, illuminating the aftermath of the collision with brilliant energy. Interestingly, while the stars in colliding galaxies rarely collide directly due to the vast distances between them, the same cannot be said for their interstellar gas. When galaxies merge, their gas clouds interact, collide, and sometimes even shock, releasing enormous amounts of energy. These interactions can also funnel gas toward the central regions of the merging galaxies, feeding their supermassive black holes and igniting quasars, some of the brightest objects in the universe. This highlights the intricate connection between galactic tides, star formation, and the growth of black holes, a relationship that continues to be a key area of research. As galaxies interact and merge, they also shed light on the larger-scale structure of the universe. Galaxy mergers are not isolated events, they are influenced by the surrounding cosmic environment. For example, in galaxy clusters, where thousands of galaxies are packed into a relatively small volume, interactions are more frequent and often more violent. These clusters are shaped by the gravitational pull of dark matter, which acts as a cosmic scaffold around which galaxies form and evolve. The study of galactic tides in such environments provides crucial insights into the role of dark matter in the formation of large-scale cosmic structures. One particularly intriguing phenomenon related to galactic tides is the formation of ring galaxies. These rare structures are thought to result from a specific type of collision in which a smaller galaxy passes directly through the center of a larger galaxy. The resulting gravitational shockwaves compress the gas and stars in the larger galaxy, creating a ring of intense star formation that ripples outward like a cosmic wave. Ring galaxies are not only visually stunning but also serve as a testament to the intricate mechanics of galactic interactions. On an even grander scale, galactic tides play a role in shaping the cosmic web, the vast network of filaments, walls, and voids that make up the large-scale structure of the universe. Galaxies are not evenly distributed throughout the cosmos. They are arranged along these filaments, with clusters forming at their intersections. The movement of galaxies along these filaments is influenced by both gravity and the tidal forces exerted by nearby structures. This interplay helps to explain the distribution of galaxies and the dynamics of galaxy clusters, shedding light on the evolution of the universe as a whole. Galactic tides also influence the smaller-scale processes that shape individual galaxies. For example, they can strip away the outer layers of gas from galaxies, a process known as ram pressure stripping. This occurs when a galaxy moves through a dense medium, such as the intracluster gas in a galaxy cluster. The resulting tidal forces can remove gas from the galaxy, effectively halting star formation and transforming it into a red and dead galaxy. This process is particularly common in dense environments, where interactions between galaxies and their surroundings are more frequent and intense. Despite our growing understanding of galactic tides, many mysteries remain. For instance, how do these processes vary across different cosmic epochs? In the early universe, when galaxies were more numerous and closer together, interactions were likely more common and more chaotic. By studying distant galaxies, we can glimpse the effects of galactic tides during this formative period of cosmic history. Advances in technology, such as the James Webb Space Telescope, are providing unprecedented views of these distant galaxies, offering new opportunities to study their interactions and evolution. Another area of ongoing research is the role of magnetic fields in galactic tides. While gravity is the primary driver of these interactions, magnetic fields can also influence the distribution and movement of gas within galaxies. These fields can shape the structures created by tidal forces, such as tails and bridges, adding another layer of complexity to the study of galactic interactions. Understanding the interplay between gravity and magnetism in these processes could provide new insights into the fundamental forces that govern the universe. As we continue to unravel the mysteries of galactic tides, we are reminded of the interconnected nature of the cosmos. The same forces that shape galaxies also govern the orbits of stars, the formation of planets, and the dynamics of galaxy clusters. By studying these interactions, we not only gain a deeper understanding of the universe but also a greater appreciation for the intricate dance of forces that has shaped it over billions of years. The story of galactic tides is far from complete. With each new discovery, we uncover more about the forces that have sculpted the universe, revealing a tapestry of interactions that span vast scales of space and time. These tidal forces, though invisible, leave behind visible marks that tell a story of creation and destruction, of chaos and order, and of a universe in constant motion. The understanding of galactic tides has also opened new windows into comprehending the life cycles of galaxies. A key concept within this framework is the idea of galaxy harassment, a phenomenon observed primarily in galaxy clusters. In these dense environments, smaller galaxies are subjected to repeated high-speed encounters with larger ones, as well as the cumulative gravitational influence of the cluster itself. Over time, these interactions strip the smaller galaxies of their gas and stars, leaving them as faint, elliptical remnants. This process highlights the role of galactic tides in shaping the morphology and fate of galaxies, particularly in crowded regions of the universe. Interestingly, it isn't a purely destructive process. It can also serve as a catalyst for star formation. When gas is compressed or funneled into specific regions of a galaxy during tidal interactions, it often triggers the birth of new stars. In this way, galactic tides act as both destroyers and creators, balancing destruction with bursts of renewal. Some astronomers even propose that the Milky Way's own history of interactions has played a role in the bursts of star formation observed in its past. On the other hand, the remnants of these interactions are sometimes more subtle, such as faint stellar streams. These streams are the leftover trails of stars from smaller galaxies or star clusters that have been pulled apart by tidal forces. Stellar streams are difficult to detect because they are often incredibly faint and dispersed over vast distances. However, they are crucial for understanding the history of a galaxy's interactions. For example, our Milky Way is surrounded by numerous stellar streams, which serve as evidence of its past mergers with smaller galaxies. These streams not only help map the gravitational influence of the Milky Way's dark matter halo but also reveal its violent past. Another fascinating area of study involves the impact of galactic tides on satellite galaxies and globular clusters. Satellite galaxies are smaller galaxies that orbit larger ones, like the Milky Way's companions, the Magellanic Clouds. Over time, tidal forces exerted by the primary galaxy can distort and even disrupt these satellites, stripping them of stars and gas. This process has significant implications for understanding the structure and composition of the primary galaxy. For instance, the stars stripped from satellite galaxies often form structures like stellar halos around larger galaxies, adding to their overall mass and luminosity. Globular clusters, which are dense collections of stars orbiting a galaxy, also experience tidal effects. As these clusters pass through a galaxy's disk or near its center, the gravitational forces can strip stars from their outer edges, forming tidal tails. These tidal interactions can reveal valuable information about the mass and gravitational potential of the host galaxy. Additionally, globular clusters serve as fossil records of the early universe, and studying their tidal interactions can provide clues about the conditions under which they formed. Zooming out to larger scales, galactic tides are instrumental in the formation and evolution of galaxy groups and clusters. Groups, such as our local group, consist of a few galaxies bound together by gravity, while clusters can contain thousands of galaxies. The interactions within these structures are governed by both the individual gravitational pulls of the galaxies and the collective influence of the cluster's dark matter halo. Over billions of years, these interactions drive the evolution of the galaxies within the cluster, leading to phenomena like galaxy mergers, tidal stripping, and the formation of intracluster light, a diffuse glow created by stars ejected during tidal interactions. One of the most dramatic examples of galactic tides at work is observed in galaxy superclusters, which represent the largest structures in the universe. These colossal formations are composed of clusters and groups of galaxies connected by filaments of dark matter and gas. Within these superclusters, the tidal forces between galaxies, clusters, and the filaments themselves create a dynamic environment where galaxies are constantly being reshaped. Studying these structures provides a glimpse into the cosmic forces that have been at play since the early stages of the universe. The interplay between galactic tides and dark matter is another frontier in astrophysics. Dark matter, which makes up the majority of the universe's matter, exerts a gravitational influence on visible matter but does not interact with it directly. The distribution of dark matter within and around galaxies significantly impacts how tidal forces shape these galaxies. For instance, the dark matter halo surrounding a galaxy can absorb or amplify the effects of tidal interactions, influencing the formation of structures like tidal tails and bridges. Observing these structures allows astronomers to map the dark matter distribution and better understand its role in galactic evolution. On a theoretical level, computer simulations have become indispensable tools for studying galactic tides. These simulations model the gravitational interactions between galaxies over billions of years, providing insights that would be impossible to gain through observations alone. By varying parameters such as galaxy mass, composition, and orbital configurations, researchers can explore a wide range of scenarios and compare the results to real-world observations. These simulations have revealed that even small differences in initial conditions can lead to vastly different outcomes, highlighting the complexity of galactic dynamics. Furthermore, these simulations have helped refine our understanding of the cosmic timeline. For example, the merging of two galaxies is not a single event but a prolonged process that can take hundreds of millions of years. During this time, the galaxies pass through multiple stages of interaction, from the initial close approach to the final coalescence. Each stage is marked by distinct phenomena, such as the formation of tidal tails, the triggering of starbursts, and the eventual settling into a new, stable configuration. These insights underscore the importance of galactic tides in shaping the evolutionary paths of galaxies. Looking ahead, future advancements in observational technology promise to revolutionize our understanding of galactic tides. Instruments like the Vera C. Rubin Observatory and space telescopes like the James Webb Space Telescope are poised to uncover new details about the interactions between galaxies. These observatories will provide deeper and more detailed views of tidal structures, including those in distant galaxies whose light has traveled billions of years to reach us. By studying these ancient interactions, astronomers hope to piece together a more complete picture of how galaxies have evolved over cosmic time. Ultimately, galactic tides remind us of the dynamic and interconnected nature of the universe. Far from being static, galaxies are constantly in motion, shaped by the gravitational forces exerted by their neighbors and the larger cosmic environment. These interactions, though often violent and chaotic, are also the engines of creation, driving the formation of stars, the growth of black holes, and the evolution of galaxies themselves. They are a testament to the intricate and ever-changing nature of the cosmos, offering a glimpse into the forces that have shaped our universe from its earliest moments to the present day. The intricate dance of galactic tides serves as a cosmic narrative of creation, destruction, and renewal, reflecting the relentless forces that govern the universe. As we delve deeper into this phenomenon, it becomes evident that galactic tides are not merely random occurrences. They are integral to the fabric of cosmic evolution. The interplay between gravity, matter, and energy shapes galaxies in ways that are both subtle and profound, leaving behind imprints that astronomers strive to decode. One of the more intriguing aspects of galactic tides is their role in forming peculiar galaxies. These galaxies, often irregular in shape, exhibit features that defy the neat categorization of spiral or elliptical forms. Peculiar galaxies are typically the result of significant tidal interactions or mergers. For instance, galaxies that collide head-on may lose their spiral arms and take on irregular shapes, or they might merge into a single elliptical galaxy. The unusual forms of peculiar galaxies often serve as a visual record of their tumultuous past, showcasing distorted structures, disrupted star clusters, and regions of intense star formation. The antennae galaxies, one of the most famous examples of galactic interaction, illustrate the dramatic effects of tidal forces. When two galaxies began their collision, their respective gravitational fields pulled streams of stars and gas into vast arcs resembling antennae. Within these tidal tails, regions of compressed gas sparked the formation of new stars, resulting in vibrant, young stellar clusters. The antennae galaxies provide a snapshot of the ongoing transformation driven by galactic tides, demonstrating how these forces can simultaneously create and destroy. In some cases, galactic interactions can lead to the formation of ring galaxies. These striking structures occur when one galaxy passes through the center of another, creating rippling effects much like a stone dropped into a pond. The gravitational disruption compresses gas in the outer regions, triggering a burst of star formation in a circular pattern. Ring galaxies are rare but visually captivating, offering unique insights into the mechanics of galactic interactions. Another phenomenon associated with galactic tides is the fueling of supermassive black holes. At the centers of most galaxies lie these colossal entities, with masses millions or even billions of times that of the Sun. During tidal interactions, gas and dust from the galaxies are funneled toward their centers, providing the material needed to feed the black holes. This accretion process often results in the black holes becoming active, emitting intense radiation and forming quasars or active galactic nuclei, AGN. These luminous objects, visible from billions of light-years away, serve as beacons of galactic evolution and are direct consequences of tidal forces. Galactic tides also influence the distribution and dynamics of dark matter. Though invisible and elusive, dark matter exerts a gravitational pull that plays a crucial role in galactic formation and interaction. The stretching and distorting of dark matter halos during tidal encounters can impact the stability of galaxies and even dictate the nature of subsequent interactions. Observing these effects provides indirect evidence of dark matter's presence and its influence on visible matter. Moreover, the study of galactic tides has profound implications for understanding the fate of the universe. On the largest scales, galaxies are not isolated. They are bound together in vast cosmic webs formed by the gravitational pull of dark matter. Over time, the interactions within these webs will determine the ultimate destiny of galaxies. In some scenarios, galactic clusters may merge to form enormous supergalaxies, while in others, galaxies may lose their gas and stars, leaving behind faint remnants. These possibilities hinge on the balance of forces at play, including the expansion of the universe and the strength of gravitational interactions. On a more immediate scale, galactic tides have practical applications in the study of our own Milky Way. The Sagittarius dwarf galaxy, for instance, is currently being torn apart by the Milky Way's gravitational forces, forming tidal streams that stretch across the sky. These streams offer a unique opportunity to map the distribution of dark matter in our galaxy, providing clues about its structure and evolution. Similarly, the ongoing interaction between the Milky Way and the Large Magellanic Cloud is expected to have significant consequences in the future, potentially triggering starbursts and altering the dynamics of our galaxy's disk. The role of advanced telescopes cannot be overstated in unraveling the mysteries of galactic tides. Instruments such as the Hubble Space Telescope and the European Southern Observatory's Very Large Telescope have captured stunning images of interacting galaxies, revealing details that were once beyond reach. These observations are complemented by data from radio telescopes, which can detect the faint emissions of gas strip during tidal interactions. Together, these tools provide a multidimensional view of the processes shaping galaxies. Looking ahead, upcoming missions like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope promise to revolutionize our understanding of galactic tides. With their ability to peer deeper into the universe and capture light from the earliest epochs of galaxy formation, these observatories will shed light on the role of tidal interactions in the early universe. They will also enable astronomers to study the faintest and most distant tidal structures, pushing the boundaries of our knowledge. Theoretical models and simulations are equally crucial in this field. By recreating the conditions under which galaxies interact, researchers can explore a wide range of scenarios and predict the outcomes of specific tidal encounters. These simulations have revealed that galactic interactions are not isolated events but part of a continuous cycle. The remnants of one merger often serve as the seeds for future interactions, illustrating the interconnected nature of the universe. In many ways, galactic tides are a microcosm of the cosmic forces that govern our universe. They embody the delicate balance between chaos and order, destruction and creation. Through their study, we gain not only a deeper understanding of galaxies but also a greater appreciation for the complexity and beauty of the cosmos. As humanity continues to explore the universe, the study of galactic tides will remain a cornerstone of astrophysics. These interactions, though distant and often invisible to the naked eye, are fundamental to the story of the cosmos. They remind us that even in the vastness of space, everything is connected, bound by the universal force of gravity. Galactic tides remind us that galaxies are not solitary entities. They exist within a dynamic cosmic web, intricately connected by the gravitational interplay that shapes their structures and destinies. These interactions showcase the grand tapestry of the universe, where every star, cluster, and tidal stream plays a role in the ongoing saga of creation and transformation. One of the most fascinating consequences of galactic tides is their role in redistributing matter within and beyond galaxies. When galaxies pass close to one another, their mutual gravitational attraction stretches and distorts their shapes. This redistribution of mass often results in the creation of tidal streams, long, thin trails of stars and gas ejected into intergalactic space. These streams, though faint and diffuse, are vital for understanding the evolutionary history of the galaxies involved. They act as celestial fingerprints, preserving evidence of past interactions long after the galaxies have moved apart or merged. Tidal streams are not just relics of past events, they are active participants in the ongoing evolution of galaxies. As these streams settle back into their host galaxies or merge with neighboring systems, they introduce new material that can trigger waves of star formation. This process is especially pronounced in gas-rich tidal streams, where the compression of molecular clouds ignites the birth of new stars. These bursts of star formation often manifest as blue, luminous regions along the tidal tails, adding a visual spectacle to the cosmic dance of galaxies. Another striking feature formed by galactic tides is the tidal bridge, a direct connection of stars and gas between two interacting galaxies. These bridges often arise during the initial phases of an encounter when the galaxies are close enough to pull material from one another but not yet fully merged. Tidal bridges serve as conduits for material exchange, facilitating the transfer of gas, dust, and even stars between galaxies. This exchange can significantly alter the chemical composition and star formation activity of the galaxies involved, leaving lasting imprints on their evolution. Tidal tails, streams, and bridges are not just visual markers of galactic interaction, they also provide crucial insights into the dark matter that pervades the universe. The behavior of these structures under the influence of gravity offers indirect evidence of the dark matter halos enveloping galaxies. By studying the shapes, lengths, and dynamics of tidal features, astronomers can infer the distribution and density of dark matter, shedding light on one of the most enigmatic components of the cosmos. The long-term effects of galactic tides extend beyond individual galaxies. Over time, repeated interactions can lead to the formation of galactic clusters and superclusters, massive structures containing hundreds or thousands of galaxies bound together by gravity. These clusters serve as laboratories for studying the collective behavior of galaxies under the influence of tidal forces. Within these clusters, galactic tides often strip smaller galaxies of their stars and gas, a process known as tidal stripping. The remnants of these stripped galaxies, often reduced to faint stellar cores, become integrated into the cluster's overall structure. The study of galactic tides also has profound implications for understanding the future of our own galaxy. The Milky Way is currently on a collision course with the Andromeda Galaxy, its nearest large neighbor. This interaction, predicted to occur in about 4 billion years, will be governed by the same tidal forces that shape other galactic encounters. The gravitational pull between the two galaxies will stretch and distort their structures, creating tidal tails and bridges while triggering massive waves of star formation. Eventually, the Milky Way and Andromeda will merge into a single, larger galaxy, transforming their combined destinies in the process. While the prospect of such a collision might seem catastrophic, it is important to note that the vast distances between stars make direct stellar collisions exceedingly rare. Instead, the primary effects of galactic mergers are structural and dynamical, reshaping the galaxy's overall morphology and triggering starburst activity. For astronomers, the impending merger offers a unique opportunity to study the mechanics of galactic interactions up close, using our galaxy as a case study for understanding these universal processes. On a larger scale, galactic tides also influence the behavior of galaxy groups and clusters. In regions where galaxies are densely packed, such as the Virgo cluster or the Coma cluster, tidal interactions occur frequently, resulting in a wide variety of outcomes. Some galaxies are completely disrupted, their stars and gas dispersed into the intracluster medium, while others grow larger and more massive through mergers. These processes contribute to the hierarchical nature of cosmic structure formation, where smaller systems coalesce into larger, more complex entities over time. Galactic tides even play a role in the distribution of intracluster light, the diffuse glow of stars scattered throughout galaxy clusters. This light, composed of stars stripped from galaxies during tidal interactions, provides valuable information about the history of these clusters. By mapping the intracluster light, astronomers can reconstruct the sequence of mergers and interactions that shape the cluster, offering a glimpse into the past dynamics of the universe. As we continue to explore the mysteries of galactic tides, it becomes clear that these forces are not merely destructive, they are also creative. Through their interactions, galaxies recycle and redistribute material, sparking new waves of star formation and fostering the growth of cosmic structures. This duality underscores the interconnected nature of the universe, where every act of destruction paves the way for new beginnings. The study of galactic tides is a testament to the power of observation and imagination. From the first glimpses of interacting galaxies through ground-based telescopes to the detailed simulations that recreate their dynamics, our understanding of these processes has grown exponentially. Yet there is still much to learn. As new telescopes and instruments come online, they will reveal even more about the intricate dance of galaxies, uncovering details that challenge our current models and expand our knowledge. Ultimately, the story of galactic tides is the story of the universe itself, a tale of constant change, bound by the forces of gravity and time. It is a reminder that even in the vast emptiness of space, there is beauty, complexity, and a profound sense of connection. Through the study of these cosmic interactions, we not only unravel the mysteries of the cosmos but also deepen our appreciation for the intricate web of forces that shape our place within it. The intricate ballet of galaxies, choreographed by gravitational forces, is a powerful reminder of the interconnectedness of the universe. Galactic tides provide a vivid example of how even the most massive structures in the cosmos influence and transform one another. As we delve deeper into this phenomenon, we uncover not only the mechanisms driving these interactions but also the larger implications for the evolution of the universe itself. One of the most profound insights from the study of galactic tides is the role they play in shaping the morphology of galaxies. Spiral galaxies, with their elegant arms and central bulges, and elliptical galaxies, with their more uniform, spheroidal shapes, often owe their forms to the cumulative effects of tidal interactions. For instance, spiral galaxies involved in close encounters may have their arms stretched and distorted, resulting in the formation of irregular shapes or even transforming into elliptical galaxies over time. These morphological changes highlight the dynamic and ever-evolving nature of galaxies, emphasizing that their current appearances are merely snapshots in a much longer evolutionary process. The creation of starburst galaxies is another striking outcome of galactic tides. During interactions, the gravitational forces compress vast clouds of gas and dust within the galaxies, triggering an intense period of star formation. These starburst events can produce hundreds or even thousands of new stars in a relatively short time, dramatically altering the appearance and composition of the galaxies involved. Starburst galaxies often shine brightly in infrared and ultraviolet wavelengths, making them some of the most luminous objects in the universe. These bursts of activity provide crucial clues about the interplay between gravity, gas dynamics, and star formation. Moreover, the material ejected during tidal interactions often forms giant arcs and loops that persist for billions of years. These structures, known as stellar streams, are particularly common around massive galaxies, such as the Milky Way. Stellar streams are thought to originate from smaller galaxies or star clusters that have been gravitationally disrupted. Their orbits and properties offer unique insights into the distribution of dark matter in the host galaxy, acting as natural tracers of the underlying gravitational potential. Galactic tides also have a profound impact on the interstellar and intergalactic medium. When galaxies interact, their gas reservoirs often become highly turbulent and heated, leading to the expulsion of material into the surrounding space. This process enriches the intergalactic medium with heavy elements, or metals, forged in the cores of stars. These metals, once expelled, play a crucial role in cooling the gas and facilitating the formation of new galaxies and stars elsewhere. This cyclical process highlights the interconnected nature of galactic ecosystems and the role of tidal forces in cosmic recycling. One of the most compelling aspects of galactic tides is their ability to create hybrid structures, blending characteristics of multiple galaxies. Polar ring galaxies, for example, are a fascinating result of such interactions. These rare systems feature a ring of stars, gas, and dust that orbits perpendicular to the main plane of the galaxy. The origin of these structures is often attributed to the accretion of material from a smaller galaxy, captured and reoriented by tidal forces. These hybrid galaxies serve as natural laboratories for studying the complex interplay of dynamics, star formation, and accretion. While much of our understanding of galactic tides comes from observational astronomy, computational simulations have also been instrumental in unraveling their complexities. By modeling the gravitational interactions between galaxies, scientists can recreate the formation of tidal tails, streams, and other structures, testing theoretical predictions against real-world data. These simulations have revealed surprising details, such as the sensitivity of tidal features to the initial conditions of the galaxies, including their masses, relative velocities, and orbital parameters. Looking ahead, the study of galactic tides is poised to enter a new era with the advent of advanced observational tools. The James Webb Space Telescope, JWST for instance, is expected to provide unprecedented views of interacting galaxies, allowing astronomers to study their structures and dynamics in exquisite detail. Similarly, next-generation surveys like the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, will map the faintest tidal streams and bridges across vast swathes of the sky, offering new opportunities to uncover hidden interactions. As we unravel the mysteries of galactic tides, we also gain a deeper appreciation for the interconnected processes that shape the universe. These forces, while destructive in some contexts, are ultimately a testament to the creativity inherent in cosmic evolution. They remind us that the universe is not static but a vibrant and dynamic system, constantly reshaping itself through the interplay of gravity, matter, and energy. Galactic tides also hold personal significance for humanity, as we consider our place in the cosmos. The Milky Way, a relatively unremarkable galaxy in the grand scheme of things, is itself shaped by these forces. The Sagittarius dwarf galaxy, for example, is currently being torn apart by the Milky Way's gravity, with its stars forming a sprawling tidal stream around our galaxy. This ongoing interaction offers a window into the kinds of processes that have shaped our galaxy's history and will continue to do so in the future. In the distant future, as the Milky Way and Andromeda approach their inevitable collision, galactic tides will once again play a central role. While this event is billions of years away, its effects are already being modeled and studied, offering a glimpse into the long-term fate of our galaxy. This merger will likely create a new, larger galaxy, sometimes referred to as Milkomeda, blending the stars and material from both systems into a new cosmic entity. Ultimately, the study of galactic tides is more than just an exploration of astrophysical phenomena. It is a journey into the interconnectedness of the universe. These forces, governed by the fundamental laws of gravity, demonstrate how seemingly isolated systems are inextricably linked, shaping one another in profound and often unexpected ways. By studying these interactions, we not only deepen our understanding of the cosmos but also gain insight into the universal principles that govern all matter, from the smallest particles to the largest galaxies. In this grand cosmic narrative, galactic tides are both sculptors and storytellers, weaving together the past, present, and future of the universe. They remind us that even in the vast emptiness of space, there is a profound sense of connection, a reminder that everything is part of a larger whole. As we continue to explore and understand these forces, we uncover not only the secrets of the cosmos but also our own place within it. As we continue to delve into the intricacies of galactic tides, it's essential to consider the role of these forces in shaping the future of galaxies, star systems, and even entire clusters of galaxies. The ongoing gravitational dance between galactic neighbors is a reminder that the universe is not a static, immutable place. Everything within it is constantly evolving, driven by forces that are both predictable and mysterious. One of the critical outcomes of galactic tidal interactions is the process of galaxy mergers. Over long periods, galaxies can collide, merge, and fuse into larger, more massive structures. This process is not as violent as it may seem at first glance. While the immense gravitational forces at play certainly cause significant disruptions in the structure of each galaxy, the vast distances between stars mean that direct collisions between individual stars are rare. Instead, the gas, dust, and dark matter within the galaxies interact in a far more significant way. The merging of two galaxies can trigger waves of star formation, as the gas is compressed and ignites new stars in a phenomenon known as a starburst. The merger of two galaxies can also have a profound effect on the overall structure of the resulting galaxy. Some mergers lead to the creation of elliptical galaxies, which are often the result of two spiral galaxies coming together. The collision causes the stars to scatter in such a way that the once well-ordered spiral structure is disrupted, and the galaxy takes on a more uniform, rounded shape. On the other hand, other mergers can preserve some of the spiral structure, though they might still result in significant changes, including the formation of new arms or the development of a central bulge. The long-term evolution of galaxies and clusters, known as galactic clusters, is also significantly influenced by tidal forces. Within these clusters, galaxies interact not only with one another but also with the vast amounts of dark matter that fill the space between galaxies. These interactions can lead to the stripping of gas from galaxies, a process known as ram pressure stripping. When a galaxy moves through the dense intergalactic medium of a cluster, the pressure from the gas in the cluster can strip away the galaxy's own gas, effectively halting star formation. This process can drastically alter the evolutionary path of the affected galaxy, preventing it from forming new stars and causing it to fade over time. Similarly, tidal forces within galaxy clusters can lead to the creation of structures like tidal tails, long streams of stars and gas that are stretched out behind interacting galaxies. These tails can extend over vast distances, sometimes hundreds of thousands of light years. The stars and gas in these tails are drawn into long, delicate filaments as a result of the gravitational forces exerted by the interacting galaxies. These tidal tails offer astronomers an invaluable tool for studying the history of galaxy interactions, as they can be used to trace the paths and motions of galaxies within a cluster. Another critical aspect of galactic tidal interactions is the role of dark matter. The study of galactic tides has provided indirect evidence of dark matter's existence, as it is believed to make up a significant portion of the mass in a galaxy. Dark matter does not interact with light in the same way that ordinary matter does, so it cannot be directly observed. However, its presence can be inferred by observing the gravitational effects it has on visible matter. In galaxy interactions, dark matter plays a crucial role in shaping the outcome of tidal forces. The gravitational pull of dark matter can distort the orbits of galaxies and influence the structure of tidal features such as tails and bridges. The collision of galaxies also provides an interesting context for the study of black holes. Every large galaxy, including our own Milky Way, is thought to harbor a supermassive black hole at its center. When galaxies collide, these supermassive black holes are eventually drawn toward one another, eventually merging in a violent and energetic event. The merging of black holes releases enormous amounts of energy in the form of gravitational waves, ripples in spacetime that can be detected by specialized instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO. These mergers of supermassive black holes are not only significant in terms of their effects on the galaxies themselves but also provide valuable insights into the nature of gravity, black holes, and the fabric of spacetime itself. But perhaps one of the most exciting aspects of galactic tidal interactions is their potential to help us understand the larger-scale structure of the universe. On the grandest scales, the universe is made up of vast cosmic structures known as the cosmic web. These structures consist of galaxies, clusters of galaxies, and dark matter filaments that are interconnected by enormous voids of empty space. Tidal interactions between galaxies within these larger structures can offer clues about the underlying forces shaping the evolution of the cosmos. For example, by studying the way in which galaxies interact within a cosmic filament, astronomers can learn more about the distribution of dark matter, the expansion of the universe, and even the mysterious force known as dark energy, which is accelerating the expansion of the cosmos. These interactions are not limited to the immediate surroundings of our own galaxy. The Milky Way, for instance, is currently in the process of interacting with the Andromeda Galaxy, a larger spiral galaxy located about 2.5 million light-years away. In about 4.5 billion years, the Milky Way and Andromeda will collide, eventually merging into a single, larger galaxy. While this event is still far in the future, the tidal forces at play are already having a noticeable effect on both galaxies. The Milky Way is currently in the process of absorbing the Sagittarius dwarf galaxy, a smaller satellite galaxy, which has been pulled apart by the tidal forces of our own galaxy. These events provide us with a snapshot of the long-term evolutionary processes that will shape the fate of galaxies in the future. In addition to their scientific value, the study of galactic tides also holds significant philosophical and existential implications. The dynamic, ever-changing nature of galaxies reminds us that the universe is in a constant state of flux. Just as galaxies evolve, so too does the universe itself. Every interaction, every collision, and every tidal effect is part of a much larger cosmic narrative that spans billions of years. The study of these phenomena can inspire a sense of awe and wonder, reminding us that we are part of an immense, interconnected cosmos. Galactic tides provide us with more than just an understanding of the mechanics behind galaxy formation and evolution. They offer a glimpse into the future of our own galaxy and provide a deeper appreciation for the vastness and complexity of the universe. The more we learn about these cosmic interactions, the more we begin to see our place in the grand scheme of things, not just as passive observers, but as participants in the ongoing evolution of the cosmos. As we continue our exploration of galactic tides and their far-reaching effects, we come to a crucial realization. The cosmic dance of galaxies is not just about what happens in the present but also about the past. Understanding how galaxies interact, collide, and evolve is like piecing together a puzzle of the universe's history. The gravitational forces between galaxies are not just passive. They actively shape the universe's very structure, offering clues to events that unfolded billions of years ago. In this context, one of the most fascinating phenomena related to galactic tides is the creation of tidal bridges. Tidal bridges are long, narrow streams of stars, gas, and dust that connect two galaxies as they interact. These bridges are created when the gravitational pull between two galaxies is strong enough to cause one galaxy to pull material from the other. This material forms a bridge of sorts, often stretching across tens or even hundreds of thousands of light years. Tidal bridges are typically temporary structures, existing only for a brief period in the life of a galaxy. However, in that time, they can serve as a snapshot of the forces at play during a galactic interaction. The formation of tidal bridges offers a wealth of information to astronomers. By studying these bridges, scientists can trace the motions and gravitational interactions between galaxies. These structures act as a cosmic fingerprint, revealing details about the past orbits, speeds, and directions of the galaxies involved. Furthermore, the study of tidal bridges helps us understand the rate at which galaxies exchange material, such as gas and dust, during interactions. This process can have a profound impact on star formation and the overall chemical evolution of galaxies, providing important insights into how galaxies evolve over time. Tidal bridges also offer clues about the distribution of dark matter within galaxies. Because dark matter interacts with gravity but not with light, it doesn't emit, absorb, or reflect any electromagnetic radiation. This makes it invisible to conventional telescopes, leaving astronomers to study it indirectly by observing its gravitational effects. The way in which tidal bridges form and evolve can reveal how dark matter is distributed within the galaxies involved. Since dark matter makes up a significant portion of a galaxy's mass, understanding its distribution is crucial to understanding the overall structure and behavior of galaxies. The intricate dance of tidal interactions does not always lead to the smooth formation of bridges or tails. Sometimes, the gravitational forces between galaxies can lead to more chaotic and violent events. In some cases, these interactions result in the complete disruption of a galaxy's structure, leading to the creation of what are known as remnant galaxies. These remnants are the remains of galaxies that have been torn apart by tidal forces during a galactic collision or merger. Unlike regular galaxies, which have a well-defined structure, remnants often appear as a diffuse cloud of stars and gas, with little to no visible organization. These remnants can offer important clues about the end stages of galactic evolution and the ultimate fate of galaxies in the universe. Galactic mergers, too, are a key aspect of understanding the role of tidal forces in galaxy evolution. These mergers are often depicted as dramatic, cataclysmic events, but the reality is far more complex. When two galaxies collide, they often pass through each other, with their stars barely interacting. Instead, it's the gas and dust within the galaxies that are more likely to collide, triggering waves of star formation. These waves, known as starbursts, are some of the most intense periods of star formation in a galaxy's history. Over time, the galaxies involved in a merger may eventually settle into a new configuration, often leading to the formation of a new, more massive galaxy. However, this process is not always smooth. The resulting galaxy may experience significant changes in its structure, with some features being preserved and others being completely wiped out. In some cases, the merger of two galaxies can lead to the formation of a massive elliptical galaxy, which is typically devoid of the spiral arms that characterize galaxies like the Milky Way. In other cases, the resulting galaxy may retain some of its original spiral structure, though it may have a more diffuse and irregular shape. The end result of a galactic merger often depends on several factors, including the relative masses of the galaxies involved, the angle of their collision, and the presence of dark matter. Some mergers lead to the formation of a single, more massive galaxy, while others may result in the creation of multiple smaller galaxies. This process of galactic merger and evolution is ongoing throughout the universe, contributing to the large-scale structure of the cosmos. As we look farther into the future, the Milky Way's interaction with the Andromeda Galaxy provides an exciting, though distant, example of what may happen when two galaxies collide. While this event is billions of years away, it serves as a valuable point of reference for understanding how galactic mergers unfold. Over time, the Milky Way and Andromeda will likely pass through each other multiple times before finally merging into a single, larger galaxy. During this process, the gravitational forces at play will shape the evolution of both galaxies, leading to the formation of new stars, the disruption of old structures, and the eventual creation of a more massive galaxy. The Milky Way-Andromeda collision also highlights another important aspect of galactic interactions: the role of galaxy clusters. Galaxy clusters are groups of galaxies that are bound together by gravity. Within these clusters, galaxies are constantly interacting with one another, with tidal forces acting as a key driver of their evolution. The dynamics of galaxy clusters are complex, with galaxies not only interacting with each other but also with the large amounts of dark matter that fill the space between them. The study of these interactions is essential for understanding the formation and evolution of galaxies on the largest scales. The study of galactic tides is not limited to just the galaxies themselves. These interactions also have a profound impact on the intergalactic medium, the vast expanse of gas and dust that fills the space between galaxies. As galaxies move through this medium, they can cause shocks and compression, triggering the formation of new stars or the heating of gas. These processes can influence the overall evolution of the cosmos, providing insights into the conditions that led to the formation of galaxies in the first place. Looking further ahead, it's clear that galactic tides will continue to play a critical role in the future of the universe. As galaxies collide, merge, and interact, they will shape the evolution of the cosmos in ways that we are only beginning to understand. The study of these interactions offers a glimpse into the future of our own galaxy and the potential fate of the universe itself. In the grand scheme of things, galactic tides serve as a reminder that the universe is constantly changing, evolving, and reshaping itself. These forces, invisible to the naked eye but felt in the very fabric of space-time, are responsible for the creation of galaxies, the birth of stars, and the eventual death of galaxies. They offer a glimpse into the long-term evolution of the universe, one that spans billions of years and will continue for eons to come. Understanding these cosmic forces not only deepens our appreciation for the complexity of the universe but also inspires a sense of wonder at the beauty and vastness of the cosmos. As we delve deeper into the mysteries of galactic tides, it's important to recognize how these interactions shape not just individual galaxies but entire cosmic structures. While we've discussed tidal tails, bridges, and mergers, these phenomena also act as significant markers in the large-scale evolution of the universe. They tell the story of how galaxies grow, transform, and eventually reach their final state. One of the most fascinating aspects of galactic tides is their ability to act as a bridge between the known and unknown aspects of cosmic evolution. When galaxies interact and undergo mergers, the effects extend beyond their visible components. The collision of gas clouds can trigger intense star formation, leading to a burst of new stars in the center of a galaxy. In fact, the interaction of galaxies, particularly during mergers, can significantly enhance the rate of star formation, creating what's known as a starburst galaxy. These galaxies are marked by their rapid and intense star creation, which is often triggered by the tidal forces that occur during such encounters. The gravitational disruptions from a nearby galaxy can compress gas clouds to the point of collapse, sparking the formation of new stars at an accelerated rate. This process of starburst formation is a clear example of how galactic tides can have an immediate, dramatic effect on a galaxy's evolution. The same tidal forces that pull stars and gas from a galaxy can, paradoxically, foster the birth of new stars. However, this process doesn't come without its downsides. The high rate of star formation in starburst galaxies can lead to the rapid consumption of their gas reserves. Once this gas is depleted, star formation slows dramatically, and the galaxy enters a quieter phase of its evolution. These post-starburst galaxies often end up as red, dead, or dying systems, lacking the fuel necessary for future star formation. In the context of galactic mergers, the effects on the gas and dust are even more pronounced. When two galaxies collide, their interstellar gas clouds can merge and mix, triggering new patterns of star formation. This process can continue for millions of years after the initial collision. However, as we've seen in some of the most famous galaxy collisions, the end result of this interaction is often the formation of a new, more massive galaxy. This galaxy might be elliptical, with a smooth, round shape, rather than the spiral arms that characterize its predecessor. The merging process often erases the previous structures of the involved galaxies, creating a new entity with its own distinct properties. While galactic tides and mergers may seem like chaotic, random events, they are part of a larger, predictable cosmic cycle. Galaxies are not static entities. They evolve over time, changing shape, size, and composition through gravitational interactions with other galaxies. Over billions of years, galaxies may undergo several rounds of mergers and tidal interactions, each of which reshapes them further. These interactions leave behind traces in the form of tidal features, such as tails, bridges, and remnants, that serve as clues to the past and future of these galactic systems. In addition to shaping the galaxies themselves, tidal forces also play a crucial role in the evolution of the surrounding cosmic environment. The gas and dust ejected during these galactic interactions often play a pivotal role in the formation of new galaxies or the growth of existing ones. For example, as galaxies collide, some of the gas ejected may be pulled into nearby galaxies, enhancing their growth and contributing to the formation of new stars. The complex interplay of forces involved in these interactions also influences the behavior of galaxy clusters, the largest known structures in the universe. Galaxy clusters are home to hundreds or even thousands of individual galaxies, each interacting with its neighbors. These interactions, driven by tidal forces, are responsible for the evolution of clusters over time. As galaxies within clusters pass by each other, they experience gravitational interactions that can lead to the stripping of gas and stars. This process, known as galaxy harassment, can leave galaxies with fewer stars, a disrupted shape, or even cause them to be expelled from the cluster entirely. The study of these interactions helps astronomers understand how galaxies are influenced by their larger cosmic environment. One of the most intriguing aspects of galactic interactions is how they shape the large-scale structure of the universe. The formation of clusters, superclusters, and voids is largely governed by the tidal forces between galaxies. Over time, these forces have shaped the universe into a vast network of interconnected structures, with galaxies and clusters forming the nodes and the vast voids between them acting as the spaces in between. The study of galactic tides is, therefore, not just a way to understand the evolution of individual galaxies, but also the formation of the universe itself. As we consider the larger scale of the universe, the role of dark energy becomes increasingly important. Dark energy is the mysterious force that is driving the accelerated expansion of the universe. While dark energy is not directly related to galactic tides, it plays a crucial role in shaping the future of the universe. The expansion of the universe, driven by dark energy, is gradually increasing the distance between galaxies. This means that, over the long term, galactic tides may become less common as galaxies move further apart. However, before this happens, the tidal forces at play in galactic mergers and interactions will continue to shape the universe for billions of years to come. We also need to consider how galactic tides influence the presence and behavior of supermassive black holes at the centers of galaxies. Most large galaxies, including the Milky Way, are thought to harbor supermassive black holes at their cores. These black holes can have a profound effect on their surrounding galaxies, particularly when tidal forces are at play. During a galactic merger, the central black holes of the involved galaxies often end up in close proximity to one another, potentially resulting in a merger of these black holes. This process, known as a black hole merger, can release an enormous amount of energy in the form of gravitational waves, ripples in spacetime that were first detected by the LIGO Observatory in 2015. The merger of supermassive black holes is one of the most dramatic events in the universe, and it is often accompanied by intense gravitational waves that ripple through the fabric of spacetime. These events provide an exciting opportunity for scientists to study the properties of black holes and the nature of spacetime itself. As we continue to refine our understanding of black hole mergers and their connection to galactic interactions, we gain deeper insights into the most extreme environments in the universe. Ultimately, the study of galactic tides serves as a powerful tool for understanding the universe's larger structure and evolution. The tidal forces that act between galaxies are not only responsible for shaping individual galaxies, but also play a role in the formation of galaxy clusters and the overall architecture of the cosmos. These interactions leave behind traces in the form of tidal tails, bridges, and remnants, each of which offers clues about the past, present, and future of the universe. By studying these interactions, astronomers are piecing together the story of the universe, one gravitational interaction at a time. As we continue to explore the fascinating nature of galactic tides, it's important to further understand the role that these interactions play on a cosmic scale. As we've seen, the tidal forces produced during galaxy mergers are not merely isolated phenomena. They are indicative of larger processes that govern the evolution of galaxies and the universe as a whole. The beauty of this interaction lies in the fact that it allows us to witness the dynamic, ever-changing nature of the cosmos in real time. Another aspect of galactic tides that remains a topic of intense interest among astronomers is the creation of tidal dwarf galaxies. These small galaxies, which form as a result of tidal interactions during galaxy collisions, are one of the most intriguing consequences of galactic tides. When two galaxies collide, the tidal forces at play can pull material from the galaxies into long streams of gas, dust, and stars. In some cases, the densest regions of these streams can collapse under their own gravity, forming new, compact galaxies known as tidal dwarfs. Tidal dwarf galaxies are fascinating for several reasons. First, they provide an opportunity to study galaxy formation in a relatively simple context. Unlike regular galaxies, which are often composed of a complex mix of stars, gas, dust, and dark matter, tidal dwarfs are often made up of only the most basic ingredients: gas, dust, and stars. Their formation in the chaotic environment of a galaxy merger gives scientists insight into how galaxies might have formed in the early universe, where tidal forces would have played a crucial role in shaping the nascent cosmic structures. What's even more intriguing about tidal dwarfs is their potential to survive over long timescales. While many tidal features are short-lived, the formation of a stable tidal dwarf galaxy represents a rare and remarkable occurrence. These galaxies can persist for billions of years, evolving much like any other galaxy, albeit on a much smaller scale. They often appear in the aftermath of major galaxy mergers, suggesting that tidal forces play an important role not just in the disruption of galaxies but in their creation as well. Tidal dwarf galaxies are also valuable in understanding the larger processes of galactic evolution. By studying the properties of these small, isolated systems, astronomers can gain insight into the early stages of galaxy formation and the role of tidal interactions in shaping galactic structures. In particular, tidal dwarfs provide a useful comparison to more massive galaxies, allowing scientists to study the processes that govern the formation and evolution of galaxies of all sizes. The presence of these tiny galaxies offers an additional layer of complexity to our understanding of the universe's structure, revealing that even the most chaotic galactic mergers can have lasting effects on the cosmos. As we reflect on the role of galactic tides in shaping the universe, we also need to consider how these interactions might influence the future of our own galaxy, the Milky Way. In about 4.5 billion years, the Milky Way is on a collision course with the Andromeda Galaxy, the largest member of our local group of galaxies. This impending collision will have profound consequences for both galaxies, with tidal forces playing a central role in the event. As the Milky Way and Andromeda begin to interact, their gravitational pull will distort each other, creating tidal tails, bridges, and other features characteristic of galactic collisions. The ultimate outcome of this collision will likely be the merger of the two galaxies, leading to the formation of a single, larger galaxy. The process will trigger a new round of star formation, potentially altering the stellar populations of both galaxies. However, despite the dramatic nature of this collision, astronomers believe that the impact on individual stars will be minimal. The vast distances between stars means that direct collisions between them are unlikely. Instead, the greatest effects will be on the gas and dust within the galaxies, which will be compressed, triggering new waves of star formation. The merger between the Milky Way and Andromeda is just one example of how galactic tides influence the long-term evolution of galaxies. Similar interactions are happening across the universe, with galaxies undergoing a never-ending cycle of gravitational interactions, mergers, and transformations. As we study these cosmic events, we gain a deeper understanding of the forces that shape the universe and the future of our own galaxy. Beyond the direct effects on galaxies themselves, galactic tides also play a role in shaping the distribution of dark matter in the universe. Dark matter, which makes up about 85% of the matter in the universe, interacts with ordinary matter only through gravity. This means that the distribution of dark matter in galaxy mergers and interactions is heavily influenced by tidal forces. When two galaxies collide, their dark matter halos, the invisible regions surrounding galaxies where dark matter resides, also interact and merge. The interplay between dark matter and tidal forces is still a topic of active research, but it is believed that these interactions can lead to the redistribution of dark matter in galaxy mergers. For example, during a collision, the gravitational forces exerted by the galaxies can distort the dark matter halos, causing them to merge or form new structures. This redistribution can have important implications for the dynamics of galaxies and galaxy clusters, as the presence of dark matter influences the overall gravitational pull of a system. Understanding how tidal forces affect dark matter is crucial for several reasons. First, dark matter plays a key role in the formation and evolution of galaxies, as its gravitational influence helps galaxies maintain their structure. Second, studying the interaction between dark matter and tidal forces may offer new clues about the properties of dark matter itself, helping us solve one of the biggest mysteries in modern physics. Finally, the behavior of dark matter during galaxy mergers can provide valuable information about the large-scale structure of the universe and the role of dark matter in shaping cosmic evolution. As we continue to learn more about the effects of galactic tides, it becomes increasingly clear that these interactions are not just events that happen in isolation. They are part of a larger, interconnected cosmic process that governs the evolution of galaxies, clusters, and the universe as a whole. The gravitational forces that drive galactic tides are responsible for shaping the universe on the grandest scales, from the formation of stars and galaxies to the structure of galaxy clusters and the distribution of dark matter. These forces act as the sculptors of the cosmos, carving out the vast, intricate patterns that define the universe. In the coming decades, advancements in technology will allow us to observe these processes in even greater detail. New telescopes, such as the James Webb Space Telescope, are already providing unprecedented views of distant galaxies and the interactions between them. With these tools, astronomers will be able to study galactic mergers and tidal features with a level of precision never before possible, shedding light on the fundamental forces that govern the universe. The study of galactic tides offers us a unique window into the complex, dynamic nature of the cosmos. By analyzing how galaxies interact, merge, and evolve under the influence of gravitational forces, we gain valuable insights into the past, present, and future of the universe. Galactic tides are not just cosmic curiosities. They are the building blocks of the universe itself, shaping the galaxies, stars, and structures that make up the vast expanse of space. The more we delve into the intricacies of galactic tides, the clearer it becomes that these gravitational interactions are central to the ongoing evolution of the universe. As galaxies collide and interact, they continue to influence one another in profound ways, creating new structures, triggering bursts of star formation, and even altering the very fabric of space itself. These cosmic events are not only a fascinating subject for astronomers and astrophysicists, but they also serve as key elements in understanding the larger processes that have shaped, and will continue to shape, the universe for billions of years to come. As we've discussed, the merging of galaxies can lead to the formation of new stars and the triggering of massive bursts of star formation. The tidal forces involved in these interactions compress the gas and dust within the galaxies, creating conditions that are ripe for star formation. This is particularly evident in the tidal tails and bridges that form as a result of galactic collisions. These structures, which are made up of gas, dust, and stars pulled from the interacting galaxies, serve as a testament to the power of gravitational forces and the dynamic nature of the cosmos. One of the most significant aspects of galactic tides is their ability to drive the evolution of supermassive black holes. Every large galaxy, including the Milky Way, is believed to contain a supermassive black hole at its center. These black holes can have masses that are millions, or even billions, of times that of the Sun. During galaxy mergers, the gravitational forces involved can cause the supermassive black holes at the centers of the merging galaxies to interact, eventually leading to their merger. This process can release an enormous amount of energy in the form of gravitational waves and electromagnetic radiation, providing a glimpse into some of the most extreme environments in the universe. The interaction of supermassive black holes and galaxy mergers has been the subject of intense study in recent years. When two black holes from merging galaxies come close enough, they begin to orbit each other, gradually losing energy through the emission of gravitational waves. As they spiral closer together, they eventually merge, creating a single, more massive black hole. This event releases an immense amount of energy, which can be detected by observatories here on Earth. Gravitational waves, ripples in space-time caused by the acceleration of massive objects, have been one of the most exciting discoveries in modern astrophysics. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first gravitational wave signal from the merger of two black holes. Since then, LIGO and other observatories have detected numerous gravitational wave events, many of which are linked to the merging of black holes in distant galaxies. The study of these events is providing valuable insights into the nature of black holes, the dynamics of galaxy mergers, and the fundamental properties of gravity. In addition to the study of black holes, galactic tides also play a critical role in the formation of galaxy clusters. Galaxy clusters are vast collections of galaxies bound together by gravity, and they are some of the largest structures in the universe. The interactions between galaxies within a cluster can be influenced by tidal forces, leading to the formation of large-scale structures such as galaxy filaments and superclusters. Galaxy clusters are not static. They are constantly evolving as galaxies move within them and interact with one another. Galactic tides play a crucial role in this ongoing evolution, shaping the distribution of galaxies within the cluster and influencing the dynamics of the cluster as a whole. The interactions between galaxies in a cluster can lead to the formation of new galaxies, the disruption of existing galaxies, and the merging of galaxies into larger systems. These processes are part of the larger cosmic dance that shapes the universe over billions of years. The tidal forces at play within galaxy clusters can also trigger the release of hot gas, which can be detected by X-ray telescopes. This gas, which is often referred to as the intracluster medium, is heated to millions of degrees by the gravitational interactions within the cluster. The study of this gas provides valuable information about the physics of galaxy clusters and the role of tidal forces in shaping the large-scale structure of the universe. One of the most fascinating aspects of galactic tides is their ability to create long-lasting structures that can persist for billions of years. For example, tidal tails and bridges, which are created when galaxies interact, can remain visible long after the initial merger event. These structures are often composed of stars, gas, and dust that have been pulled from the galaxies during their interaction. Over time, these tidal features can evolve, with some merging into new galaxies or being scattered throughout the cosmos. The persistence of these tidal structures serves as a reminder of the far-reaching effects of galactic interactions. Even after a galaxy merger has completed, the tidal features created by the interaction can continue to influence the surrounding space, shaping the distribution of stars and gas in the region. This long-term influence highlights the importance of galactic tides in shaping the universe's larger structures and provides valuable insight into the processes that govern the evolution of galaxies. As we continue to observe and study the effects of galactic tides, we are also beginning to understand the role these interactions play in the distribution of elements throughout the universe. The collisions and mergers of galaxies lead to the creation of new stars, many of which are composed of heavier elements formed in previous generations of stars. These heavy elements, which include elements like carbon, oxygen, and iron, are essential for the formation of planets and life as we know it. The study of galactic tides, therefore, provides not only a window into the past but also a glimpse into the future. As galaxies continue to interact and evolve, they will continue to forge the elements necessary for the development of new stars and planetary systems. These processes, which have been ongoing for billions of years, will continue to shape the universe for billions more. One of the most intriguing aspects of galactic tides is their potential to reveal information about the fundamental forces that govern the universe. The interactions between galaxies, the formation of tidal structures, and the behavior of dark matter and supermassive black holes all provide valuable clues about the underlying physics of the cosmos. By studying these phenomena, astronomers can gain deeper insights into the nature of gravity, the role of dark matter, and the processes that govern the formation and evolution of galaxies. In the coming years, advancements in observational technology will allow scientists to explore these phenomena in greater detail. The James Webb Space Telescope, for example, is expected to provide unprecedented views of distant galaxies and their interactions. With its advanced infrared capabilities, Webb will be able to peer through dust and gas clouds, revealing the inner workings of galaxy mergers and tidal features in ways that were previously impossible. As we continue to study the effects of galactic tides, we gain a deeper understanding of the universe's most fundamental processes. From the formation of galaxies and stars to the evolution of galaxy clusters and the behavior of dark matter, the tidal forces that shape the cosmos are key to understanding the past, present, and future of the universe. These interactions, which have been ongoing for billions of years, serve as a testament to the dynamic nature of the universe and the ever-changing forces that govern it. Galactic tides are one of the most fascinating and important phenomena in the universe. They shape the evolution of galaxies, trigger bursts of star formation, and influence the distribution of dark matter and supermassive black holes. These tidal forces have played a central role in the formation of galaxies, clusters, and the large-scale structure of the universe. As we continue to study these interactions, we gain valuable insights into the nature of the cosmos and the forces that govern it. Galactic tides, as we've seen, are more than just curious phenomena. They are essential mechanisms for the shaping and transformation of galaxies, and ultimately, the universe. When we zoom in on their intricate processes, they reveal the unseen forces at play, the interconnectedness of cosmic structures, and the perpetual evolution of galaxies over time. But what does the future hold? As technological advancements progress, we will be able to explore these galactic interactions with greater precision. In addition to the groundbreaking observations from the James Webb Space Telescope, upcoming missions and instruments like the next generation of gravitational wave detectors and radio telescopes are poised to shed even more light on the dynamics of galactic collisions and their aftermath. This will allow us to observe, in real time, the interactions that create these tidal forces, mergers of galaxies, supermassive black hole collisions, and the formation of new cosmic structures. It will bring us closer to answering fundamental questions about the nature of our universe. How do galaxies evolve from these interactions? What do these tidal features tell us about the behavior of dark matter or dark energy? And most intriguingly, how do galactic tides contribute to the ongoing cycle of creation, destruction, and rebirth in the cosmos? Another important facet of this cosmic dance lies in understanding the role of dark matter during galactic interactions. Dark matter, which makes up a significant portion of the universe's total mass, cannot be seen directly with conventional telescopes. However, its presence can be inferred through gravitational effects on visible matter. In the context of galactic tides, dark matter can play a pivotal role in shaping the outcomes of galactic mergers and interactions. Dark matter is thought to form vast halos that surround galaxies, exerting a gravitational pull on the visible matter within the galaxies. These halos are not uniform, and as galaxies interact, the behavior of dark matter can influence the dynamics of the collision. For instance, when two galaxies merge, the dark matter halos surrounding each galaxy can interact with one another, potentially leading to the formation of a more massive dark matter structure. This interaction can also affect the distribution of stars and gas within the galaxies, further complicating the evolution of the galactic system. In some cases, the gravitational forces involved in galactic mergers can result in the dispersal of dark matter into intergalactic space, forming new structures that could shape future galactic interactions. Understanding the role of dark matter in these tidal interactions is one of the most pressing questions in modern astrophysics. It could provide new insights into the fundamental nature of dark matter and how it interacts with ordinary matter, as well as how these interactions shape the universe on large scales. This is where simulations and computational models become crucial. As astronomers attempt to map the behaviors of galactic mergers, supermassive black holes, and dark matter, powerful supercomputers are used to simulate the various forces and interactions that take place during these events. These simulations are vital in providing a virtual laboratory for studying galactic tides and their consequences. They allow scientists to test their theories, predict future events, and uncover aspects of galactic evolution that would otherwise remain hidden. By simulating galaxy collisions, the resulting tidal effects, and the dynamics of dark matter, astronomers can recreate the processes that took place billions of years ago during the formation of our galaxy and others. These models help to answer questions about the origins of our galaxy, the fate of the Milky Way in its eventual collision with the Andromeda Galaxy, and the long-term evolution of galaxy clusters and superclusters. Looking ahead, one of the most exciting aspects of galactic tidal interactions is their potential to illuminate the nature of galaxy formation itself. The interplay between galaxies, their gas, dark matter, and supermassive black holes holds the key to understanding how galaxies grow and evolve over time. From the formation of early galaxies in the distant universe to the complex, interconnected systems we observe today, galactic tides play an instrumental role in this process. In particular, the study of tidal interactions can provide insights into the process of galaxy recycling. Just as matter is recycled within galaxies through stellar evolution and supernova explosions, the material from tidal features such as bridges and tails may eventually be reincorporated into new galaxies, forming fresh stars, nebulae, and even new black holes. This ongoing cycle of formation and destruction not only highlights the cosmic connections between galaxies but also demonstrates the dynamic, ever-changing nature of the universe. Furthermore, the influence of galactic tides is not restricted to just the galaxies involved in the interaction. These forces can have a ripple effect across large cosmic scales, impacting neighboring galaxies, galaxy clusters, and even the distribution of matter in the broader universe. Tidal forces from one galaxy can create disturbances in the nearby intergalactic medium, a vast space between galaxies that is often filled with diffuse gas. These disturbances can alter the conditions in this intergalactic space, triggering new phenomena such as the formation of new galaxies or the dispersal of existing ones. The study of tidal features is, therefore, not just about understanding individual galaxies or even galaxy clusters. It's about examining how the gravitational pull of one galaxy can affect the larger cosmic web, a vast interconnected structure that stretches across the entire universe. In this sense, galactic tides are a manifestation of the universal laws of gravity, extending their influence far beyond the galaxies they originate from. One of the lesser discussed yet incredibly intriguing effects of galactic tides is their role in the evolution of galactic morphology, the shape and structure of galaxies. Galaxies come in various shapes, from the spiral galaxies like our Milky Way to elliptical and irregular galaxies. These shapes are not static. They evolve over time in response to external influences, including tidal interactions. When galaxies interact gravitationally, their shapes can be altered in profound ways. For example, a spiral galaxy like the Milky Way might undergo a transformation into an elliptical galaxy after multiple tidal interactions or mergers. These tidal forces stretch and distort the shape of the galaxies, changing the orientation of their stars, gas, and dark matter, which ultimately affects their overall appearance. Over time, these morphological changes accumulate, giving rise to new types of galaxies and altering the large-scale structure of the universe. As galaxies continue to evolve and interact, they may go through multiple cycles of distortion and reshaping. The tidal forces that act upon them are not one-time events. They are ongoing and can continue to reshape galaxies for billions of years. This constant evolution of galactic structure speaks to the dynamic, ever-changing nature of the universe, where nothing remains fixed or static. One thing is abundantly clear: the universe is a dynamic, constantly evolving system, where galaxies interact, merge, and transform in ways that we are only beginning to understand. Galactic tides are not just a cosmic curiosity, they are a fundamental part of the universe's evolutionary process. They shape the galaxies we see today and will continue to shape the galaxies of tomorrow. The future of our understanding of galactic tides is bright. With new technologies and observatories on the horizon, we will be able to peer even deeper into the universe, observing the intricate dance of galaxies and the tidal forces that govern their evolution. Whether we are studying the formation of new galaxies, the behavior of dark matter, or the role of supermassive black holes, the gravitational interactions between galaxies will continue to be a key area of research for years to come. As we continue to uncover the mysteries of galactic tides, we move closer to understanding the forces that shape not just individual galaxies but the entire universe. The more we learn, the more we realize how interconnected everything is, from the smallest particles of dark matter to the largest galaxy clusters. Galactic tides are just one example of how the universe is in constant motion, constantly evolving, and constantly surprising us with the beauty and complexity of its cosmic dance. The gravitational interactions between galaxies through galactic tides are not just fascinating to study for their immediate effects but also for the long-term consequences they hold for the evolution of the cosmos. As we venture deeper into these interactions, we find that these phenomena hold a crucial role in the grander scheme of cosmic structure formation and transformation. One key aspect of galactic tidal interactions that is often overlooked is how these forces contribute to the distribution and behavior of gas and dust in the universe. The galaxies we observe today contain enormous clouds of gas and dust, which serve as the raw material for the formation of new stars and planetary systems. However, the structure of these clouds is not static. They are constantly being disturbed and reshaped by external forces, particularly gravitational interactions between galaxies. Tidal interactions can stretch, compress, and redistribute these gas and dust clouds, potentially triggering new star formation events or even causing the gas to be expelled from the galaxy entirely. This redistribution of material plays a vital role in the overall star formation rate of galaxies, as the gas clouds that collapse under tidal forces may form new generations of stars. However, the fate of this material is not always predictable. In some cases, it may be stripped away by the tidal forces, leaving the galaxy with a reduced supply of gas to form future stars. What's even more intriguing is that tidal interactions don't just affect gas clouds in one galaxy. They can impact the intergalactic medium, the sparse gas and dust that exists between galaxies. This intergalactic medium plays a significant role in the process of galactic accretion, where galaxies draw in material from their surroundings to fuel growth. Tidal forces from interacting galaxies can stir up the intergalactic medium, increasing its density and potentially providing a source of material for galaxies to accrete. In this sense, galactic tidal interactions are not just reshaping individual galaxies. They are playing an active role in the very process that drives the growth of cosmic structures. This material exchange between galaxies, whether through tidal tails, bridges, or the stripping of gas, creates a complex feedback loop where galaxies influence one another in a delicate dance. By triggering star formation, redistributing material, and reshaping the intergalactic medium, these tidal forces are central to the ongoing evolution of the universe. Beyond just the direct effects on galaxies, tidal interactions also have a far-reaching influence on the larger-scale structure of the universe. Galaxies do not exist in isolation. They are part of vast cosmic networks known as galaxy clusters. These clusters, composed of hundreds to thousands of galaxies, are bound together by gravity and have their own complex dynamics. Tidal forces from interactions within these clusters can influence the formation of substructures such as galaxy groups, galaxy pairs, and even vast cosmic filaments. In some cases, galaxies within a cluster may be drawn toward each other by tidal forces, leading to mergers that create even more massive galaxies. In other cases, galaxies may be ejected from the cluster altogether due to gravitational interactions with other members. These processes contribute to the formation and evolution of galaxy clusters, which are among the largest structures in the universe. By understanding how tidal forces shape galaxy clusters, we can gain insight into how the universe's largest-scale structures are organized and evolve over time. The effect of galactic tides on supermassive black holes is another critical area of investigation. Supermassive black holes, which lie at the centers of most large galaxies, exert a profound influence on their host galaxies. These black holes can accrete vast amounts of gas, generating immense amounts of energy in the process. When galaxies interact and merge, their supermassive black holes can also merge, releasing a significant amount of energy in the form of gravitational waves. These events are some of the most energetic phenomena in the universe, and studying them can provide invaluable insights into both the behavior of black holes and the gravitational interactions that govern galaxy evolution. In some cases, the tidal forces generated by galaxy interactions can also lead to the growth of supermassive black holes. When two galaxies collide, the material from the outer regions of each galaxy is funneled toward the center, where it can feed the supermassive black holes, increasing their mass. This process can trigger an intense burst of energy, known as an active galactic nucleus, AGN, which is often visible as a bright and powerful source of radiation. These events are some of the most spectacular manifestations of galactic tides, highlighting the profound influence these forces have on the inner workings of galaxies. One of the most exciting prospects in studying galactic tides is the potential for uncovering the role of dark energy in these interactions. While we know that dark energy is responsible for the accelerated expansion of the universe, its exact properties remain a mystery. The study of galactic tides could provide a unique window into understanding how dark energy behaves at large scales. By observing how galaxies interact and how tidal forces shape their evolution, scientists may be able to gain indirect insights into the properties of dark energy and its role in the cosmos. The study of galactic tides also intersects with the search for life beyond our galaxy. While tidal interactions themselves are unlikely to directly affect the potential habitability of planets in distant galaxies, the processes they trigger could play a role in the conditions necessary for life to arise. For example, tidal forces that trigger the formation of new stars could also lead to the formation of planets in the habitable zone, the region where life-supporting conditions might exist. Additionally, galactic mergers and interactions could influence the stability of planetary systems, potentially affecting the long-term habitability of planets. While these interactions may seem distant and abstract, they represent an essential component of the universe's overall process of cosmic evolution. Just as the Earth experiences the influence of tidal forces from the Moon, galaxies are constantly being shaped by the gravitational interactions that occur between them. These tidal forces not only affect the shape and structure of galaxies but also influence the broader cosmic environment in which they exist. Understanding these processes can help us piece together the complex puzzle of the universe's evolution and our place within it. One of the most remarkable aspects of galactic tides is how they remind us of the interconnectedness of all things in the universe. The gravitational pull of one galaxy can have a profound impact on the evolution of neighboring galaxies. Galaxies can trigger new star formation in other galaxies, and tidal interactions can alter the trajectory of entire galactic clusters. In a sense, galactic tides show us that galaxies are not isolated islands in space. They are part of a vast and intricate web of gravitational interactions, each influencing the other in subtle and powerful ways. This realization brings us to a deeper philosophical reflection on the nature of the cosmos. The universe, in its infinite vastness, is not a series of independent, isolated systems, but rather a dynamic and interconnected whole, where every action has a ripple effect that extends far beyond what we can observe. The gravitational interactions between galaxies, though seemingly local, are part of a much larger cosmic dance, a dance that spans the entire universe and shapes the very fabric of existence itself. The study of galactic tides is a testament to the complexity and beauty of the universe. It shows us how, through the simple force of gravity, galaxies are continuously evolving, merging, and transforming. These processes are not just fascinating to study, they are fundamental to understanding how the universe functions on a large scale. As we continue to explore the mysteries of galactic tides, we move closer to unlocking the secrets of the cosmos, from the birth of galaxies to the eventual fate of the universe itself. The study of galactic tides offers an essential glimpse into the broader mechanisms of the universe, where we are constantly uncovering how galaxies evolve and interact through these powerful gravitational forces. As we continue to unravel the cosmic dance of galaxies, there's much more to explore, especially the various types of interactions that occur between galaxies, each one contributing to the larger evolutionary process in different ways. The very nature of galactic tidal interactions can lead to a variety of outcomes depending on the mass, velocity, and trajectory of the galaxies involved. For example, when two galaxies collide or pass close to each other, the tidal forces can pull their shapes into distorted configurations. This can result in a phenomenon called a tidal disruption, where a galaxy's structure is pulled apart. These interactions can also lead to the formation of tidal tails, long streams of stars, gas, and dust that are stretched out by the gravitational pull of the other galaxy. These tidal tails can be incredibly dense in certain areas, creating regions ripe for new star formation. These newly born stars may contribute to the galaxy's overall growth, or be scattered into the intergalactic medium. These tidal tails are not just beautiful, glowing streaks of light visible in some of the most stunning images of space. They also offer scientists a critical insight into how galaxies grow and evolve. Tidal tails are evidence of the material exchanged between galaxies during an interaction, and studying them allows astronomers to better understand the ways in which galaxies accrete material over time. The stars, gas, and dust that get swept into these tails may be absorbed by the galaxies involved, enriching their composition, or they could become part of a new galaxy entirely, potentially forming a new galactic structure or even triggering the formation of a new galaxy. Another fascinating outcome of galactic tidal interactions is the formation of tidal bridges, which are created when the gravitational pull of two galaxies causes gas and stars to connect between the galaxies. These bridges can act as conduits of material, allowing gas to flow from one galaxy to another. Tidal bridges can be viewed as temporary features in the cosmic landscape, but they have lasting effects on the galaxies they connect. Over time, material from these bridges may be funneled into the galaxies, contributing to their growth. In some cases, the bridge may even help set the stage for a full-fledged galactic merger, where two galaxies collide and merge into a single, more massive galaxy. These tidal bridges and tails contribute to the overall dynamism of the universe, showing us that galaxies are not static objects, but rather they are constantly interacting with one another, exchanging material and changing shape. Galactic interactions are not just isolated events but are part of the broader ongoing processes that shape the cosmos. In fact, mergers between galaxies are one of the most intriguing aspects of galactic tides. When two galaxies come together under the influence of their mutual gravity, they can merge into a single, more massive galaxy. These mergers can result in profound changes in the structure, star formation rate, and even the central black hole of the newly formed galaxy. Over the course of billions of years, this process of galactic mergers and interactions has played a significant role in the formation of the galaxies we observe today. The details of how these mergers occur can vary. Some galaxies merge slowly over time, while others collide at high velocities, resulting in spectacular cosmic events. These collisions can trigger intense bursts of star formation, known as starbursts, as the gas and dust in the galaxies is compressed. This leads to the creation of new stars at a rapid rate. However, the fate of the stars in the colliding galaxies is not always predictable. Some may be ejected from the newly formed galaxy, while others may become part of its core. The merger can also cause the central supermassive black holes of the two galaxies to merge, releasing massive amounts of energy in the process. This merging of black holes is one of the most extreme events in the universe and is accompanied by the release of gravitational waves, ripples in spacetime that travel across the cosmos. While the collision of galaxies can result in the formation of new stars and the growth of supermassive black holes, it is also a highly disruptive process. The merging galaxies can undergo significant changes in their structure, sometimes resulting in the formation of elliptical galaxies. These galaxies are typically more rounded and have less defined structures than their spiral counterparts. The violent nature of a galactic merger can strip away much of the gas and dust in a galaxy, leaving behind a system composed mainly of older stars. Despite the destruction and disruption caused by galactic mergers, they are an essential component of galactic evolution. The Milky Way itself has likely undergone multiple mergers over the course of its history, and it is predicted to eventually merge with the Andromeda Galaxy in about 4 billion years. This future merger will significantly alter the structure of both galaxies, eventually forming a larger elliptical galaxy. This process of galactic accretion, where smaller galaxies are absorbed by larger ones, has played a key role in the growth of the largest galaxies in the universe. As we study galactic tidal interactions, we also gain a greater understanding of the role of dark matter in these processes. Dark matter, the mysterious substance that makes up a significant portion of the mass of the universe, plays a critical role in shaping the gravitational interactions between galaxies. While we cannot directly observe dark matter, its presence can be inferred from its effects on visible matter. In the case of galactic mergers, dark matter halos surrounding each galaxy help to govern the gravitational forces at play during interactions. These dark matter halos influence how galaxies collide, how their stars and gas are redistributed, and how the final structure of the merged galaxy will be shaped. The interactions between dark matter and normal matter during galactic tidal events may help explain some of the strange and unexplained phenomena observed in the universe. For example, some galaxies appear to rotate at speeds that cannot be explained by the visible mass alone. This discrepancy can be attributed to the presence of dark matter, which helps to explain the gravitational forces that govern these galaxies' motion. As we delve deeper into the complexities of galactic tides and their effects, we also begin to realize how the study of these interactions helps us understand the fundamental forces that govern the universe. Gravitational forces, which we experience here on Earth as a familiar force that keeps us grounded, play a central role in shaping the evolution of galaxies, stars, and entire cosmic structures. The study of galactic tides reveals the intricate web of gravitational interactions that govern the behavior of the cosmos on the largest scales. Through the lens of galactic tides, we also gain a deeper appreciation for the interconnectedness of the universe. The cosmos is not just a collection of isolated systems, but a vast network of interactions and influences, where the actions of one galaxy can have profound effects on its neighbors. This interconnectedness extends beyond galaxies, reaching into the intergalactic medium, dark matter, and the fabric of spacetime itself. Galactic tides are far more than just gravitational interactions. They are a vital force that shapes the evolution of the universe. From tidal tails and bridges to galaxy mergers and the growth of supermassive black holes, the impact of these interactions is profound and far-reaching. As we continue to study these cosmic phenomena, we gain valuable insights into the processes that govern the formation and evolution of galaxies, the role of dark matter, and the ultimate fate of the universe. The study of galactic tides is still in its early stages, and there is much more to learn. As technology advances and our understanding of the universe deepens, we may uncover even more mysteries about how galaxies interact and evolve. These discoveries will not only help us understand the past and present of our own galaxy, but will also offer a glimpse into the future of the cosmos itself, where galaxies will continue to dance to the rhythm of gravity, creating new structures and new possibilities in the vast expanse of space. As we continue exploring the remarkable effects of galactic tides, it's important to realize that these cosmic phenomena don't just affect the large, easily observable structures like galaxies. They also have far-reaching implications for the smaller components within those galaxies, particularly stars, star clusters, and the interstellar medium. One of the most fascinating aspects of galactic tidal interactions is how they influence star formation. When two galaxies approach each other, the tidal forces at play can compress gas and dust in the galaxies, initiating a burst of star formation. This is known as a starburst event, and it can lead to the creation of massive clusters of stars, all formed in a relatively short period of time. These bursts of star formation can drastically alter the life cycles of the galaxies involved. In some cases, the interaction may trigger the rapid formation of new stars, while in others, the gas and dust can be stripped away, potentially leading to a decrease in the rate of star formation. These starburst events often have a lasting impact on the structure and behavior of galaxies. For instance, if a galaxy experiences a prolonged starburst, the energy output from the new stars can heat up the surrounding gas, preventing further star formation and leaving the galaxy with a reduced capacity to create new stars. On the other hand, if the starburst is intense and short-lived, it may accelerate the galaxy's evolution, pushing it toward a new phase of its life cycle. These rapid shifts can contribute to the transformation of galaxies from spiral systems into ellipticals, especially if the tidal interaction is part of a larger merger process. In addition to the creation of new stars, galactic tidal forces can also influence the behavior of existing stars within galaxies. When two galaxies come into close proximity, the gravitational forces can tug at the stars, altering their orbits and velocities. Some stars may be ejected from the galaxy altogether, particularly if they are located on the outer edges of the galaxy and are swept up in the tidal forces. These ejected stars may travel through intergalactic space, becoming part of the larger cosmic background. Interestingly, the study of these ejected stars, often referred to as intergalactic stars, has opened up new questions about the fate of stars after they are expelled from their home galaxies. Some of these stars may join other galaxies, while others may drift through the voids between galaxies, remaining isolated and adrift in the vast emptiness of space. These intergalactic stars are a reminder of the dynamic and ever-changing nature of the universe, where even the most established objects can be displaced and transformed by the gravitational forces at play. The effects of galactic tides on star formation and stellar behavior are not confined to just the interacting galaxies. These interactions can also influence the intergalactic medium, the diffuse gas that fills the space between galaxies. When two galaxies pass close to one another, the gas in the intergalactic medium can be drawn into the galaxies through tidal forces, enriching the galaxies with new material. This influx of gas can provide the raw material for future star formation or can add to the mass of the galaxy, potentially altering its gravitational influence on surrounding objects. This interplay between galaxies and the intergalactic medium highlights the broader role that galactic tides play in the evolution of the universe. Galaxies are not isolated systems but are deeply interconnected with their surroundings. The gravitational interactions that drive galactic tides not only shape the galaxies themselves but also the material in between. Over time, These interactions create a feedback loop, where the galaxies and the intergalactic medium influence each other in ways that are still being studied by astronomers and cosmologists. Another intriguing aspect of galactic tidal interactions is how they contribute to the growth and evolution of supermassive black holes. At the center of most galaxies, including our own Milky Way, lies a supermassive black hole. These black holes are not just passive objects, they play an active role in the dynamics of the galaxy. When galaxies interact and merge, the supermassive black holes at their cores are also affected by the tidal forces at play. In some cases, these black holes may be drawn toward each other and eventually merge, releasing an immense amount of energy in the form of gravitational waves. The merging of supermassive black holes is one of the most powerful events in the universe, and it has been the subject of much research in recent years. These mergers are thought to occur relatively frequently in the universe, especially in regions where galaxies are densely packed, such as in galaxy clusters. The resulting gravitational waves from these mergers travel across the universe, providing us with a unique opportunity to study the most extreme events in the cosmos. The detection of gravitational waves from supermassive black hole mergers is one of the most exciting achievements in astrophysics, offering a new way to observe and understand the universe. These supermassive black holes also play a crucial role in regulating the growth of galaxies. The immense gravitational pull of a black hole can influence the movement of stars and gas within the galaxy, shaping its overall structure. In some cases, the energy released by a black hole can prevent the galaxy from forming new stars by heating up the surrounding gas, creating a sort of cosmic feedback loop. This interaction between supermassive black holes and their host galaxies highlights the delicate balance between creation and destruction in the universe, where forces of gravity, energy, and matter are constantly in flux. While galactic tidal interactions often result in the creation of new stars, the exchange of material, and the eventual merging of galaxies, these processes also lead to the destruction of older galactic structures. As galaxies collide and merge, much of their original gas and dust can be stripped away, especially in the outer regions. This stripping process can lead to the formation of dark galaxies, which are galaxies that lack significant amounts of gas and dust and are composed mostly of stars. These dark galaxies are thought to be the remnants of earlier galactic interactions, and they provide valuable insight into the end stages of galactic evolution. The creation of dark galaxies is just one example of how galactic tides can lead to the transformation and even destruction of galaxies. As galaxies collide and evolve, their structures can change in profound ways. Some galaxies may lose much of their gas and dust, becoming quiescent systems that are no longer capable of forming new stars. Others may be completely consumed by the tidal forces of larger galaxies, ultimately disappearing into the vast cosmic expanse. As we continue to explore the mysteries of galactic tides, we are reminded that the universe is constantly in a state of flux. Galaxies are not static objects. They are dynamic systems that evolve over billions of years, shaped by the gravitational forces that govern their interactions. These tidal forces create stunning structures like tidal tails, bridges, and tidal disruptions, but they also drive the fundamental processes that govern the growth and decay of galaxies. The study of galactic tides is essential for understanding how galaxies form, evolve, and ultimately reach their end stages. The interplay between gravitational forces, dark matter, star formation, and supermassive black holes continues to reveal new and fascinating insights into the workings of the universe. With each discovery, we gain a deeper appreciation for the complexity and beauty of the cosmos, where galaxies are constantly interacting, merging, and evolving in a cosmic dance that stretches across time and space. The study of galactic tides is far from over, and as technology advances, we will continue to uncover new details about these incredible phenomena. Whether we are observing the formation of tidal tails, tracking the merger of supermassive black holes, or studying the intricate dynamics of galactic interactions, each discovery brings us one step closer to understanding the true nature of the universe. As we look to the future, it is clear that the study of galactic tides will play a crucial role in our understanding of the cosmos. The forces that shape galaxies are the same forces that govern the evolution of stars, planets, and even life itself. By exploring these gravitational interactions, we are not just studying distant galaxies, we are gaining insights into the very nature of the universe itself. As we continue our journey through the intricacies of galactic tidal interactions, another fascinating aspect comes into focus: the role of dark matter. This mysterious substance, which constitutes a significant portion of the universe's mass, has a profound effect on how galaxies interact with each other. Though dark matter cannot be directly observed, its presence is inferred from its gravitational influence on visible matter, including stars, gas, and even light itself. When galaxies interact through tidal forces, dark matter plays a crucial role in shaping the outcome of these interactions. Dark matter does not interact with light or electromagnetic radiation, which makes it invisible to conventional observation. However, its gravitational pull affects the motion of galaxies, and it is often responsible for the distribution of mass within galaxies and galaxy clusters. This unseen component of the universe is thought to exist in large halos surrounding galaxies. These halos can influence the tidal forces that galaxies exert on each other. In many cases, the presence of dark matter halos alters the trajectory and extent of tidal interactions, making them more complex and unpredictable than they would otherwise be. When two galaxies collide or pass close to one another, their dark matter halos also interact. The interaction of these halos can result in the formation of gravitational waves, which ripple through space-time. These waves carry information about the dark matter distribution in galaxies and have become a key area of research in astrophysics. By studying these gravitational waves, scientists can learn more about the distribution and properties of dark matter, providing us with valuable insights into one of the greatest mysteries in modern science. Moreover, the dark matter halos of galaxies can also affect the way tidal forces influence the galaxy's visible matter. As the gravitational pull of a nearby galaxy tugs at the dark matter halo, it can distort the galaxy's shape, causing visible features such as tidal tails and bridges to form. However, the behavior of the dark matter does not always align perfectly with the visible matter of the galaxy. In some cases, the dark matter may be displaced from the galaxy's core during interactions, leaving the visible matter in a different configuration. This misalignment between the visible matter and dark matter may be one of the reasons why some galactic interactions appear chaotic or distorted. In addition to the effects of dark matter, galactic tides also influence the behavior of cosmic gas, particularly in the case of galaxy mergers. During a merger, the gas and dust within each galaxy are often funneled toward the center of the new, combined galaxy. This influx of gas can fuel the formation of a central supermassive black hole, as the material is drawn inward by the intense gravitational forces of the merging galaxies. The merging process, aided by tidal forces, may also trigger an active galactic nucleus, AGN, a highly energetic region at the center of a galaxy powered by the supermassive black hole. AGNs are often associated with intense bursts of radiation and can outshine the rest of the galaxy, sometimes producing visible jets of material that extend far beyond the galaxy itself. The study of tidal interactions in merging galaxies offers clues to the behavior of supermassive black holes. These interactions can provide the necessary conditions for black holes to grow by accreting material. It is thought that during mergers, the two supermassive black holes located at the centers of the colliding galaxies may spiral toward each other, eventually merging into a single, more massive black hole. This process is accompanied by the release of an extraordinary amount of energy in the form of gravitational waves, ripples in spacetime that propagate through the universe. The detection of these waves by advanced observatories such as LIGO and Virgo has opened up a new field of astrophysical research, providing direct evidence of black hole mergers and confirming some of the predictions made by Einstein's theory of general relativity. The eventual merger of two supermassive black holes can have far-reaching consequences for the galaxy in which they reside. The merging black holes may disrupt the surrounding stars and gas, creating a more chaotic and energetic environment. This disruption may also lead to the ejection of stars from the galaxy, a phenomenon known as a hypervelocity star. These stars are accelerated to such high speeds that they are expelled from their host galaxy, never to return. Hypervelocity stars offer valuable insights into the extreme conditions produced by galactic interactions, as well as the dynamics of supermassive black holes. While galactic tidal forces can lead to dramatic events like star formation bursts, black hole mergers, and the creation of tidal structures like tails and bridges, they also play a critical role in the long-term evolution of galaxies. Over billions of years, the interactions between galaxies gradually shape their final form. In some cases, these interactions may result in the complete disruption or even the destruction of the galaxies involved. As galaxies collide and merge, they may lose much of their original gas and dust, and their stars may be scattered across intergalactic space. The study of galactic tidal interactions also offers a window into the future of our own Milky Way galaxy. Our galaxy is on a collision course with the Andromeda Galaxy, our closest large neighbor. In about 4 billion years, the Milky Way and Andromeda are expected to merge, triggering a series of tidal interactions that will radically transform both galaxies. During the collision, stars and gas from each galaxy will be redistributed, leading to the creation of a new, larger galaxy. This merger is expected to create a galaxy with an elliptical or irregular shape, with the central supermassive black holes of each galaxy eventually merging into a single, more massive black hole. The interaction between the Milky Way and Andromeda will serve as a real-world example of the complex processes we've been discussing. Interestingly, the merging of the Milky Way and Andromeda may not be as catastrophic as it sounds. Despite the immense gravitational forces involved, the vast distances between stars in each galaxy mean that direct collisions between stars are extremely unlikely. Instead, the primary effects of the merger will be felt in the gas and dust, which will trigger new waves of star formation and lead to the creation of a new cosmic structure. This process will reshape the galaxies involved, creating something entirely new from the merging forces of tidal interaction. Beyond galaxy mergers, the study of galactic tides also provides valuable insights into the larger-scale structure of the universe. Galaxies do not exist in isolation. They are part of vast cosmic structures known as galaxy clusters. These clusters are made up of hundreds or even thousands of galaxies, all bound together by gravity. In these dense regions of space, galactic tidal interactions are more frequent, and the effects of these interactions are amplified. The merging of galaxies within a cluster can lead to the creation of massive galaxy ellipticals, or other unusual structures. By studying the tidal forces at play within galaxy clusters, astronomers can learn more about the distribution of dark matter and the overall dynamics of the universe. The role of galactic tides extends beyond individual galaxies and clusters. On an even larger scale, these tidal interactions may be responsible for the formation and evolution of the cosmic web, the vast network of galaxy clusters and filaments that make up the large-scale structure of the universe. The cosmic web is shaped by the gravitational forces of dark matter, with galaxies and clusters of galaxies connected by vast, tenuous filaments of gas and dark matter. Galactic tides, acting over billions of years, may help sculpt the shape of this web, guiding the motion of galaxies and the distribution of matter throughout the cosmos. As our understanding of galactic tides grows, it becomes clear that these interactions are far more than just fascinating phenomena. They are central to the evolution of the universe itself. Galactic tides play a pivotal role in shaping the formation of galaxies, the behavior of stars, and the growth of supermassive black holes. These interactions offer us a glimpse into the dynamic and ever-changing nature of the cosmos, where the forces of gravity, dark matter, and stellar evolution work in harmony to create the universe we observe today. Galactic tidal interactions are not just phenomena that shape galaxies during the course of their lifetimes. They also serve as an essential tool for astronomers to understand the deep past of the universe. By studying tidal structures like tidal tails, bridges, and even the resulting mergers, astronomers can trace the history of galactic collisions and the evolution of galaxies themselves. This deep past provides invaluable insight into the formation of the universe, the development of cosmic structures, and even the fundamental laws that govern how galaxies move and interact. One of the key aspects of studying galactic tidal interactions is the concept of time. The processes that lead to tidal tail formation, galaxy mergers, and the buildup of tidal bridges unfold over vast cosmic timescales. For example, The tidal tails created in a galactic collision might take hundreds of millions of years to fully develop, while the complete merger of two galaxies could take even longer. By studying galaxies in different stages of these processes, astronomers can piece together the timeline of galactic evolution and the dynamics that drive them. Interestingly, the specific way in which galaxies interact can tell astronomers a great deal about their internal structures. The mass, size, and distribution of stars, gas, and dark matter within a galaxy can all influence the way in which a galaxy responds to tidal forces. Some galaxies are more resilient to the effects of tidal forces due to their mass and gravitational pull, while others are more susceptible to distortions and disruptions. By carefully studying how galaxies interact, scientists can deduce the internal composition of galaxies, providing a window into their past and their future. Moreover, the study of tidal interactions is not limited to galactic mergers alone. Even when galaxies merely pass close to each other, the tidal forces involved can have long-lasting effects on both galaxies. In some cases, tidal interactions can lead to the formation of new stellar populations, as gas clouds are compressed by the gravitational forces. This process, called starburst activity, can cause an intense period of star formation, during which new stars are born at a rapid pace. These new stars are often observed as young, bright clusters, and the regions where they form can provide clues about the specific conditions of the interaction. Starbursts are a critical aspect of galactic evolution, and studying how they arise from tidal forces is one way astronomers investigate how galaxies grow and evolve. On a cosmic scale, galactic tidal interactions also help shape the large-scale structure of the universe. These interactions are one of the driving forces behind the formation of galaxy clusters, the large groups of galaxies bound together by gravity. Galaxy clusters are some of the most massive structures in the universe, and they serve as laboratories for studying the effects of gravity, dark matter, and other fundamental forces. The collisions and mergers that occur within these clusters, driven by tidal interactions, play a significant role in the overall evolution of the cluster. This, in turn, can help us understand the distribution of galaxies across the universe and the forces that govern their motion. In particular, galactic tides are often responsible for the creation of the most massive galaxies in the universe, elliptical galaxies. Ellipticals are galaxies that have a smooth, oval shape, unlike the spiral structure of the Milky Way or Andromeda. They are typically formed when several smaller galaxies merge and their gas and stars are redistributed. This process often occurs over the course of billions of years, during which the tidal interactions between the merging galaxies smooth out the galaxy's shape, eventually resulting in a massive elliptical galaxy. These galaxies can be filled with old stars, and they often lack the gas and dust needed to form new stars, leading to a more inactive appearance compared to other types of galaxies. But elliptical galaxies are not the only outcome of galactic tidal interactions. In some cases, the forces of gravity can create irregular galaxies, which have no specific shape at all. These irregular galaxies can form when galaxies collide in particularly chaotic and disorganized ways. The disruption caused by the tidal forces can prevent the galaxy from taking on any distinct shape, leaving it in an unstructured, often fragmented form. Despite their lack of order, these galaxies can still harbor vast amounts of stars, gas, and dark matter. They may also have intense star formation activity, leading to the creation of young stars, which give the galaxy a bright and active appearance. Interestingly, irregular galaxies can also provide insight into the early stages of galactic formation. It is thought that the most primordial galaxies were likely irregular in shape, lacking the structure and organization seen in more evolved galaxies. As the universe has evolved, galactic mergers and tidal interactions have gradually shaped galaxies into the more familiar forms we see today. By studying irregular galaxies, astronomers can gain a better understanding of the processes that led to the formation of the universe's first galaxies, and how these early structures evolved over time. The study of galactic tides also plays a crucial role in understanding the relationship between galaxies and their environment. Galaxies do not exist in isolation. They are part of vast cosmic structures that are influenced by the distribution of dark matter and the forces of gravity. The interactions between galaxies and the gas and dark matter surrounding them help shape their growth and evolution. Tidal forces are one of the primary mechanisms by which galaxies can exchange mass and energy with their environment. This exchange can have profound effects on the galaxy's evolution, influencing its star formation rates, its shape, and even the fate of its supermassive black hole. One area of active research in this field is the role of tidal interactions in the feedback process. Feedback refers to the way in which a galaxy's internal processes can influence its external environment. For example, the formation of stars within a galaxy can generate intense radiation and winds that can push gas out of the galaxy, a phenomenon known as galactic outflows. Tidal forces can amplify or modify these outflows, causing gas to be expelled more efficiently. This process can affect the galaxy's ability to form new stars and, in some cases, can even lead to the quenching of star formation altogether. Furthermore, the feedback from tidal interactions is often observed in galaxy clusters, where the gravitational forces between galaxies can create shock waves in the gas that fills the space between galaxies. These shock waves can heat the gas to extremely high temperatures, preventing new stars from forming. This is a key aspect of the so-called evolutionary path of galaxies within clusters, as the tidal forces present in these environments can slow down the growth of new stars, ultimately leading to the transformation of galaxies into older, more passive systems. Another fascinating area of study is the role of tidal interactions in the generation of cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. They are thought to be produced in some of the most extreme environments in the universe, including the aftermath of galactic mergers and tidal interactions. These energetic particles can be ejected into space by the violent events surrounding a galactic collision, and they can travel across vast distances, impacting everything from the intergalactic medium to the magnetic fields of distant galaxies. The study of galactic tides and their impact on cosmic rays is still in its early stages, but scientists are beginning to realize that these particles may play an important role in the evolution of galaxies and the cosmic environment. By understanding how cosmic rays are produced in tidal environments, astronomers may be able to gain a deeper understanding of the processes that drive galaxy evolution and the large-scale dynamics of the universe. As we approach the future of galactic tidal studies, one thing is certain: these interactions are a central piece of the cosmic puzzle. They not only shape the galaxies themselves but also provide insights into the fundamental forces of the universe. Whether it's the merging of galaxies, the formation of tidal structures, or the influence of dark matter, galactic tides offer a glimpse into the complex and dynamic nature of the cosmos. These interactions, driven by gravity and shaped by the invisible presence of dark matter, are the forces that have sculpted the universe into the intricate and beautiful system of galaxies that we see today. The beauty of studying galactic tides lies in their ability to reveal secrets that are otherwise hidden from view. For instance, tidal interactions can expose the presence of dark matter in galaxies, which makes up most of the universe's mass but does not emit light. When galaxies interact, their visible matter is affected by gravitational forces, but the way this matter moves and distorts also hints at the unseen influence of dark matter. By carefully analyzing these distortions, astronomers can map the distribution of dark matter in and around galaxies, providing clues about its elusive nature. Dark matter halos, the invisible cocoons that surround galaxies, play a crucial role in galactic tidal interactions. These halos are believed to extend far beyond the visible boundaries of a galaxy and interact gravitationally with other halos during galactic encounters. The sheer mass of these halos amplifies the tidal forces during interactions, shaping the resulting features like tidal tails and bridges. Understanding these halos not only deepens our knowledge of individual galaxies but also offers insights into the fundamental structure and behavior of the universe. One fascinating aspect of these interactions is their role in the creation of stellar streams. Stellar streams are elongated ribbons of stars that are often remnants of smaller galaxies or star clusters that have been torn apart by the tidal forces of a larger galaxy. These streams provide astronomers with a unique opportunity to study the gravitational environment of their host galaxy. By tracing the paths of these streams, scientists can infer the distribution of mass, including dark matter, in the host galaxy. The study of stellar streams is like unraveling a cosmic breadcrumb trail, leading to discoveries about the history and evolution of galaxies. In the Milky Way, several stellar streams have been identified, including the Sagittarius stream, which originates from a dwarf galaxy currently being consumed by our galaxy. These streams are not only beautiful to observe but also serve as a testament to the ongoing dynamic interactions that shape the cosmos. They remind us that galaxies are not static entities but are constantly in motion, influenced by the gravitational dance of their neighbors. Another intriguing consequence of galactic tidal interactions is the triggering of supermassive black hole activity. Most galaxies, including our Milky Way, harbor a supermassive black hole at their center. During a galactic collision or close encounter, gas and dust are often funneled toward the centers of the interacting galaxies. This influx of material can fuel the central black holes, causing them to become active and emit immense amounts of energy as they consume the incoming matter. These active galactic nuclei (AGN) are among the brightest objects in the universe and can outshine entire galaxies. The study of AGN triggered by tidal interactions has revealed much about the connection between galactic evolution and black hole growth. It appears that galactic mergers are one of the primary mechanisms by which supermassive black holes accumulate mass and energy. This connection between black hole activity and galactic tides underscores the interconnectedness of cosmic processes, where the interactions of entire galaxies influence the behavior of objects as small as black holes. Beyond individual galaxies, tidal interactions also shape the fate of galaxy groups and clusters. In these environments, where multiple galaxies are bound together by gravity, tidal forces are particularly intense. The gravitational pull between neighboring galaxies can strip stars, gas, and even dark matter from their hosts, redistributing this material throughout the cluster. This process, known as tidal stripping, can create diffuse halos of stars and gas around galaxy clusters, contributing to their overall mass and luminosity. In some cases, tidal stripping can even lead to the formation of orphan stars, stars that have been ejected from their parent galaxies during interactions. These stars, which now drift freely through the cluster, provide a unique glimpse into the history of tidal forces within the cluster. They also contribute to the faint glow known as intracluster light, which is often observed in galaxy clusters. The study of intracluster light is a growing field in astronomy, as it offers a way to measure the total mass and structure of galaxy clusters. This light is thought to originate from stars that have been stripped from their galaxies over billions of years, creating a diffuse and faint halo around the cluster. By studying this light, astronomers can learn about the cumulative effects of tidal interactions and the overall dynamics of the cluster environment. The role of tidal interactions in shaping galaxies also extends to their chemical composition. During interactions, gas from one galaxy can be transferred to another, mixing the chemical elements within the two systems. This exchange can lead to the enrichment of certain elements in the receiving galaxy, influencing its ability to form new stars. The chemical signatures left behind by these interactions can provide a record of past encounters, allowing astronomers to reconstruct the history of galactic interactions. Interestingly, these chemical changes are not limited to the galaxies themselves. The gas expelled during tidal interactions often ends up in the intergalactic medium, the vast expanse of space between galaxies. This gas can carry heavy elements produced in stars, enriching the intergalactic medium and contributing to its overall composition. This process highlights the far-reaching effects of galactic tides, which extend beyond individual galaxies to shape the broader cosmic environment. The interplay between galaxies and their environment is further illustrated by the phenomenon of ram pressure stripping. This occurs when a galaxy moves through a dense medium, such as the gas within a galaxy cluster, at high speed. The pressure exerted by the surrounding gas can strip material from the galaxy, much like wind blowing leaves off a tree. This process is often enhanced by tidal interactions, which can weaken the galaxy's gravitational hold on its gas and stars, making them more susceptible to stripping. Ram pressure stripping can have profound effects on a galaxy's evolution. By removing gas, it can quench star formation, effectively halting the galaxy's growth. This process is thought to be one of the reasons why many galaxies in clusters are red and dead, with little to no ongoing star formation. The combination of ram pressure stripping and tidal interactions creates a complex interplay of forces that shapes the destiny of galaxies within clusters. As we continue to explore the mysteries of galactic tides, one of the most exciting developments is the advent of advanced simulations and observations. With powerful telescopes like the James Webb Space Telescope and cutting-edge computer models, astronomers can now study galactic interactions in unprecedented detail. These tools allow scientists to simulate the gravitational dance of galaxies, predicting how they will evolve over billions of years. They also enable the detection of faint tidal structures that were previously invisible, opening new windows into the study of galactic evolution. The future of this field holds the promise of even greater discoveries. By unraveling the complexities of galactic tides, we are not only learning about the forces that shape the universe but also gaining a deeper appreciation for the interconnectedness of cosmic phenomena. From the smallest stars to the largest galaxy clusters, the effects of tidal interactions ripple across the universe, leaving an indelible mark on its history and structure. The more we uncover about galactic tides and their far-reaching impacts, the more we realize that these gravitational interactions are central to understanding the universe's grand design. One of the emerging questions in this field involves the role of galactic tides in the formation of galaxy morphology, how galaxies take on their distinct shapes, from spirals to ellipticals to irregular forms. Observations suggest that tidal interactions, especially in dense galactic environments, often play a pivotal role in reshaping galaxies over time. For example, spiral galaxies, with their well-defined arms, can transform into irregular galaxies during close encounters or mergers. The gravitational forces involved distort the orderly spiral structure, stretching it into chaotic, elongated forms. Similarly, two merging spiral galaxies often coalesce into an elliptical galaxy, a dense, rounded system with little to no ongoing star formation. These transformations are not merely cosmetic. They alter the internal dynamics and life cycle of the galaxies, influencing everything from star formation rates to the movement of stars and gas. The elliptical galaxies resulting from mergers are especially intriguing. Unlike spirals, where stars orbit in a relatively flat plane, stars in elliptical galaxies have random orbits, resembling a swarm of bees around a hive. This randomness is a direct consequence of the violent processes that accompany galactic collisions. The blending of angular momenta and the redistribution of energy during a merger leave behind a system that lacks the ordered structure of a spiral galaxy. Another area of active research involves the creation of shell galaxies, which exhibit faint, shell-like structures surrounding their cores. These shells are thought to form when a larger galaxy tidally disrupts a smaller companion, scattering its stars into specific orbital patterns. As these stars move through their new orbits, they create overlapping shells that are often only visible under specific observational conditions. Studying these shell structures can provide valuable insights into the mass and shape of the larger galaxy, as well as the history of the interaction that created them. The gas dynamics during galactic interactions add another layer of complexity. Gas behaves differently from stars due to its ability to dissipate energy through processes like cooling and compression. When galaxies interact, their gas clouds often collide, triggering massive bursts of star formation. These starbursts are some of the most visually stunning events in the universe, producing clusters of young, hot, and luminous stars. However, these bursts are short-lived, typically lasting only a few million years, after which the gas supply is exhausted or dispersed. Interestingly, the starburst phase can lead to the formation of superstar clusters, or even dwarf galaxies. In some cases, the gas ejected during tidal interactions coalesces into compact regions that collapse under their own gravity, giving birth to new galaxies. These so-called tidal dwarf galaxies are unique because they form from recycled material, rather than the primordial gas that gave rise to most galaxies in the early universe. Studying these systems offers a glimpse into an alternative mode of galaxy formation, one driven by interactions rather than the isolated collapse of matter. The interactions between supermassive black holes during galaxy mergers add yet another layer of intrigue. When two galaxies merge, their central black holes eventually form a binary system, orbiting each other in a cosmic dance that can last billions of years. Over time, these black holes may merge, releasing an enormous amount of energy in the form of gravitational waves, ripples in the fabric of spacetime predicted by Einstein's general theory of relativity. Detecting these waves from merging black holes is one of the key goals of modern astrophysics, with facilities like LIGO and the upcoming LISA mission poised to make groundbreaking discoveries. The presence of binary or merging supermassive black holes also affects their host galaxies. As the black holes interact, they can stir up the surrounding gas, creating powerful jets and outflows that heat and expel the gas. This feedback process can suppress star formation, effectively halting the growth of the galaxy. Such feedback mechanisms are a cornerstone of modern galaxy formation models, as they help explain why many massive galaxies have relatively low star formation rates despite their abundance of gas. Tidal interactions also provide a natural laboratory for studying the properties of dark matter. As galaxies interact, their dark matter halos collide and distort, creating features that are observable even in the absence of visible light. For instance, the famous bullet cluster, a collision of two galaxy clusters, has revealed the separation of dark matter from ordinary matter during the interaction. This separation provides direct evidence for the existence of dark matter and offers clues about its behavior and properties. On smaller scales, individual galaxies like the Milky Way are surrounded by a halo of dark matter that extends far beyond their visible boundaries. When a smaller galaxy or dwarf galaxy passes through this halo, the tidal forces exerted by the dark matter can strip stars and gas from the smaller galaxy, creating streams and other tidal features. By studying these interactions, astronomers can map the distribution and density of dark matter in the Milky Way and other galaxies, providing critical constraints for theoretical models. One of the most enigmatic questions in this field is whether galactic interactions influence the formation of life. During a merger, the bursts of star formation can produce new planets and solar systems, some of which may be conducive to life. On the other hand, the same interactions can also disrupt existing solar systems, potentially sterilizing planets by exposing them to intense radiation or ejecting them from their host galaxies. While these effects are difficult to study directly, they highlight the profound impact that cosmic events can have on the conditions necessary for life. In the broader context of cosmic evolution, galactic tides serve as a driving force for the large-scale structure of the universe. Over billions of years, the repeated interactions between galaxies contribute to the growth of galaxy clusters and the formation of cosmic filaments, the vast, web-like structures that connect galaxies across the universe. These interactions are not random but are influenced by the underlying distribution of dark matter, which acts as a scaffolding for the visible universe. The story of galactic tides is far from over. As observational technology continues to advance, astronomers are uncovering increasingly subtle features of these interactions, from faint tidal streams to complex gas flows. Meanwhile, simulations are becoming more sophisticated, capable of modeling the evolution of galaxies with unprecedented accuracy. Together, these tools are painting a detailed picture of a universe in constant motion, shaped by the invisible hand of gravity. Ultimately, the study of galactic tides is a reminder of the interconnectedness of the cosmos. Every galaxy, no matter how isolated it may seem, is part of a larger web of interactions that stretches across the universe. These interactions, driven by the relentless pull of gravity, shape the destiny of galaxies, stars, and planets alike, leaving behind a rich tapestry of structures and phenomena for us to explore and understand. The interconnectedness of the cosmos underscores how no galaxy exists in total isolation. Even the most solitary galaxies, those lying in the quiet outskirts of galaxy clusters or the voids between them, are ultimately shaped by the gravitational currents and interactions of their cosmic neighbors. Over time, these connections play out in profound ways, influencing not only the physical structure of galaxies but also the environments they create for stars, planets, and potentially life. A particularly fascinating aspect of galactic tides is how they act as a kind of cosmic recycling program. As galaxies interact, gas and dust that might otherwise lie dormant can be compressed and re-energized, leading to the birth of new stars and even entirely new structures like dwarf galaxies. This redistribution of matter ensures that no material goes to waste. In some ways, the remnants of galactic mergers and interactions become the seeds for new cosmic growth, perpetuating the cycle of creation and destruction that defines the universe. In our own galactic neighborhood, the ongoing interaction between the Milky Way and its satellite galaxies, such as the Magellanic Clouds, provides a closer-to-home example of these processes. The Magellanic Clouds are slowly being pulled apart by the gravitational forces of the Milky Way, creating features like the Magellanic Stream, a long, trailing ribbon of gas that stretches across the sky. This stream is a vivid reminder of the dynamic relationship between the Milky Way and its satellites, as well as a source of raw material that could eventually be incorporated into new star-forming regions within our galaxy. The Andromeda Galaxy, our nearest large galactic neighbor, also plays a significant role in the future of the Milky Way. Andromeda and the Milky Way are on a collision course, set to merge in approximately 4.5 billion years. While this may sound catastrophic, it's worth noting that individual stars within the galaxies are so far apart that direct collisions between them will be exceedingly rare. Instead, the gravitational interactions will dramatically reshape both galaxies, flinging stars into new orbits and likely creating a new, larger elliptical galaxy. This future event is a testament to the inevitability of galactic interactions, even for galaxies that currently appear stable and isolated. Galactic interactions are not limited to the large-scale collisions we observe. Smaller, more subtle interactions, such as tidal stripping, also play a crucial role in shaping galaxies. When a smaller galaxy passes near a much larger one, the larger galaxy's gravitational forces can strip away stars, gas, and dark matter from the smaller galaxy. This process can leave behind tidal streams, elongated trails of stars and gas that arc across the sky. These streams serve as cosmic fingerprints, preserving a record of past interactions and allowing astronomers to reconstruct the history of galactic encounters. For example, the Sagittarius Dwarf Galaxy, a small companion of the Milky Way, is currently being torn apart by tidal forces. The remnants of this galaxy form a series of tidal streams that encircle the Milky Way, providing direct evidence of how our galaxy grows by accreting smaller systems. These streams also serve as laboratories for studying dark matter, as their precise shapes and motions are influenced by the distribution of dark matter in the Milky Way. On a larger scale, the interactions between galaxy clusters reveal even more dramatic consequences of gravitational tides. Galaxy clusters, which contain hundreds or even thousands of galaxies, are bound together by their combined gravitational pull. As clusters merge, the galaxies within them experience intense tidal forces that can strip them of their gas, quench star formation, and leave behind trails of stars and gas that stretch across the cluster. These interactions contribute to the overall evolution of clusters, transforming them into more massive and complex structures over time. The formation of tidal bridges and tails during these interactions is particularly intriguing. Tidal bridges connect galaxies that are in the process of merging, forming luminous pathways of stars and gas that span the space between them. These bridges are not permanent structures. They evolve and dissipate as the galaxies merge, but they offer a fleeting glimpse of the dynamic processes at play. Tidal tails, on the other hand, are elongated streams of stars and gas that are flung outward during close encounters. These tails can extend for hundreds of thousands of light years, serving as some of the most visually striking features of galactic interactions. What makes tidal tails especially valuable to astronomers is their longevity. While bridges may dissipate relatively quickly, tidal tails can persist for billions of years, providing a long-lasting record of past interactions. By studying these tails, astronomers can gain insights into the mass and distribution of matter within the interacting galaxies, as well as the nature of the gravitational forces that shape them. Simulations of galactic interactions have been instrumental in advancing our understanding of these phenomena. Using powerful supercomputers, astronomers can recreate the dynamics of galaxy collisions in remarkable detail, modeling everything from the motion of individual stars to the behavior of gas and dark matter. These simulations allow scientists to test hypotheses about the formation of tidal tails, bridges, and other features, as well as to predict what future interactions, such as the merger of the Milky Way and Andromeda, might look like. One of the key findings from these simulations is the realization that galactic interactions are not isolated events but part of a continuum of processes that span billions of years. From the initial approach of two galaxies to their eventual merger and the formation of a new system, every stage of the interaction is interconnected. This perspective underscores the importance of studying galactic tides not as isolated phenomena but as integral components of the broader story of cosmic evolution. Even as we uncover more about galactic tides, many questions remain unanswered. For instance, how do these interactions influence the formation of supermassive black holes and their subsequent growth? What role do galactic tides play in shaping the large-scale structure of the universe, such as the cosmic web of filaments and voids? And perhaps most intriguingly, how do these interactions impact the potential for life in the universe, either by creating new habitable environments or by disrupting existing ones? As we continue to explore these questions, it becomes clear that galactic tides are not merely a curiosity of astrophysics, but a fundamental aspect of the universe's dynamic nature. They remind us that even in the vast emptiness of space, everything is connected, bound together by the invisible threads of gravity that weave the cosmos into a single, interconnected whole. The interplay of galactic tides is like a grand cosmic symphony, where the forces of gravity orchestrate a dance of unimaginable scales. The beauty lies in how the seemingly chaotic collisions and mergers are guided by fundamental principles, resulting in structures that defy imagination. These interactions provide a window into the intricate processes shaping galaxies and the universe itself. One particularly intriguing aspect is the effect of these interactions on star formation. When galaxies interact, the gravitational forces compress clouds of gas, triggering bursts of star formation. Known as starburst galaxies, these systems shine brightly in the universe due to their rapid production of new stars. However, this process isn't without limits. The intense star formation depletes the gas reservoirs of these galaxies, leaving them unable to sustain such activity for extended periods. Essentially, the same process that breathes new life into galaxies also paves the way for their eventual decline in star-forming capabilities. In the context of galactic evolution, interactions play a pivotal role in shaping galaxies into their current forms. Spiral galaxies, with their elegant, winding arms, are often transformed into elliptical galaxies through mergers. This transformation results from the redistribution of angular momentum during collisions, which disrupts the orderly rotation of stars. The end product is a more spherical structure, characteristic of elliptical galaxies. This process highlights how galactic tides are central to the evolutionary pathways of galaxies, dictating their morphology and dynamics. The role of dark matter in these interactions cannot be overstated. While dark matter is invisible, its gravitational influence is profound. It forms massive halos around galaxies, acting as a scaffold that holds them together. During galactic collisions, dark matter halos play a crucial role in shaping the outcomes. For instance, the gravitational pull of dark matter can enhance the formation of tidal tails and bridges, while also dictating the motion of galaxies within clusters. Moreover, studying the behavior of dark matter in these interactions provides valuable insights into its elusive properties, a key mystery in modern astrophysics. One of the most awe-inspiring outcomes of galactic interactions is the formation of ring galaxies. These rare structures arise when a smaller galaxy passes directly through the center of a larger one. The resulting gravitational shockwaves propagate outward, compressing gas and triggering a circular wave of star formation. The result is a luminous ring of young stars surrounding the central core, a phenomenon that serves as a testament to the intricate dynamics of galactic tides. On the scale of galaxy clusters, interactions become even more complex. In massive clusters, galaxies are subjected to a phenomenon known as ram pressure stripping. As a galaxy moves through the hot, dense gas that permeates the cluster, the pressure effectively removes its gas, stripping it away and leaving the galaxy devoid of the raw material needed for star formation. This process is a stark reminder of how galaxies are shaped not only by interactions with each other but also by the environments they inhabit. The cosmic web, the large-scale structure of the universe, also bears the imprint of galactic tides. Filaments of galaxies and dark matter connect clusters, forming a network that stretches across the cosmos. As galaxies move along these filaments, their interactions contribute to the growth of the web, merging smaller structures into larger ones. These processes reflect the interconnected nature of the universe, where even the smallest interactions have far-reaching consequences. The study of galactic tides has also revealed unexpected phenomena, such as the creation of orphan stars. These stars are stripped from their parent galaxies during tidal interactions, left to drift through the intergalactic medium. While they may seem insignificant, these rogue stars provide unique opportunities for studying the properties of intergalactic space and the forces at play in galaxy interactions. As astronomers delve deeper into the mysteries of galactic tides, they are increasingly turning to advanced technology and innovative methods. The next generation of telescopes, such as the James Webb Space Telescope and the upcoming Extremely Large Telescope, promises to revolutionize our understanding of these processes. With their unprecedented sensitivity and resolution, these instruments will allow us to observe galactic interactions in exquisite detail, from the early stages of approach to the final coalescence of merging systems. Simulations continue to play a critical role in this research. By recreating the conditions of galaxy interactions, scientists can test hypotheses and predict outcomes with remarkable accuracy. These simulations not only shed light on the mechanisms behind tidal features but also help us understand how the universe evolved from its early chaotic state to the structured cosmos we see today. As we look to the future, the study of galactic tides remains a frontier of discovery. Each new observation and simulation adds to our understanding of the forces that shape the universe, revealing the complexity and interconnectedness of all things. These cosmic interactions remind us of the dynamic nature of the universe, where creation and destruction are two sides of the same coin, driving the evolution of galaxies and the cosmos itself. The mysteries of galactic tides are a testament to the power of gravity as a universal force. They reveal a universe in constant motion, where the interactions between galaxies create beauty, complexity, and new possibilities. As we continue to explore these phenomena, we uncover not only the secrets of galaxies but also the fundamental principles that govern the universe. The interplay of galactic tides also offers a profound perspective on the sheer timescales over which these processes unfold. While the interactions may seem sudden or dramatic when observed in isolated snapshots, they occur over millions, sometimes billions, of years. This immense timescale challenges our perception of time itself, as these events span durations far exceeding the entirety of human history. Each collision, merger, or formation of tidal structures represents a chapter in a galaxy's story, stretching far beyond anything we can directly witness. Take, for example, the famous antennae galaxies, a pair of colliding galaxies located about 45 million light-years away. Their interaction has been ongoing for hundreds of millions of years, yet it is still far from complete. The iconic tidal tails stretching outward are the result of countless gravitational interactions, pulling stars, gas, and dust into vast streams that arc through the void of space. The antennae galaxies offer a vivid glimpse into what our own Milky Way may experience when it eventually merges with the Andromeda Galaxy. This eventual collision between the Milky Way and Andromeda, predicted to occur in about 4.5 billion years, will be a defining moment in the life of our galaxy. While the vast distances between stars mean that direct collisions between them are unlikely, the gravitational forces at play will reshape both galaxies. Their spiral structures will be disrupted, and over time, they are expected to merge into a single, more massive elliptical galaxy. This cosmic event will be accompanied by bursts of star formation, as gas clouds are compressed and ignited. It's a dramatic reminder that even the serene night sky is subject to the inexorable forces of gravity and evolution. The interactions between galaxies also provide critical insights into the role of black holes in shaping galactic dynamics. At the heart of most galaxies lies a supermassive black hole, millions or even billions of times the mass of the Sun. When galaxies merge, their central black holes are drawn together, eventually forming a binary system. As these black holes spiral closer due to the loss of energy through gravitational waves, they may eventually merge into an even larger black hole. The gravitational waves produced during this process ripple across the fabric of spacetime, offering a way to study these cataclysmic events indirectly. Moreover, galactic interactions have profound implications for the chemical evolution of the universe. When galaxies collide and merge, their gas and dust are mixed together, enriching the interstellar medium with heavier elements formed in previous generations of stars. This mixing process not only fuels new star formation but also contributes to the overall chemical diversity of the universe, setting the stage for the development of planets and, potentially, life. Interestingly, not all galactic interactions result in destruction or dramatic change. In some cases, galaxies can pass close to one another without merging, creating temporary bridges of gas and stars. These bridges, while fleeting, can serve as conduits for material to flow between galaxies, influencing their evolution in subtle but significant ways. Such interactions highlight the complexity and variability of galactic tides, where no two encounters are exactly alike. The role of satellite galaxies in these interactions is another area of fascination. Many larger galaxies, including the Milky Way, are surrounded by smaller satellite galaxies, which are often drawn in and torn apart by tidal forces. This process, known as tidal stripping, leaves behind streams of stars and other material, which can be observed as faint, elongated structures in the outskirts of galaxies. These stellar streams serve as evidence of past interactions and provide valuable clues about the history of a galaxy's environment. In the case of the Milky Way, its satellite galaxies, such as the Magellanic Clouds, are currently interacting with it, leaving behind streams of gas and stars. The Magellanic Stream, a long ribbon of gas extending from the large and small Magellanic Clouds, is one such feature, created by the gravitational pull of our galaxy. These interactions not only affect the satellites but also influence the evolution of the Milky Way itself, contributing to its growth and star formation. Galactic tides also extend their influence to the phenomenon of galaxy harassment, a process observed in dense galaxy clusters. In these crowded environments, galaxies experience frequent close encounters with their neighbors and the cluster's gravitational potential. These interactions can strip gas and stars from galaxies, transform their shapes, and quench their star formation activity. Over time, this harassment can reduce spiral galaxies to featureless, compact systems known as dwarf spheroidal galaxies. The study of galactic tides and their effects is not merely an academic pursuit. It has profound implications for our understanding of the universe's past, present, and future. By observing and analyzing these interactions, astronomers can reconstruct the history of galaxies, uncovering the processes that shaped them over billions of years. This knowledge, in turn, helps us piece together the broader story of cosmic evolution, from the formation of the first galaxies to the complex structures we see today. As our observational capabilities continue to improve, we are likely to discover even more about the mysteries of galactic tides. Upcoming missions and instruments, such as the Nancy Grace Roman Space Telescope and the Square Kilometer Array, promise to expand our view of the universe, revealing interactions at greater distances and in unprecedented detail. These advancements will not only deepen our understanding of galactic dynamics but also inspire new questions and avenues of exploration. The interplay of galaxies, driven by the forces of gravity, is a reminder of the interconnectedness of the universe. From the smallest tidal streams to the grandest mergers, these interactions shape the cosmos in ways that are both profound and beautiful. They remind us that the universe is a dynamic, ever-changing place, where even the most massive structures are subject to the relentless pull of gravity and time. The concept of galactic tides provides a profound glimpse into the complexity and dynamism of the universe. While it might seem like galaxies are isolated islands in an endless sea of space, their interactions tell a very different story, one of connection, transformation, and constant evolution. Every tidal tail, every burst of star formation, and every faint stellar stream speaks to the gravitational interplay that shapes galaxies on a cosmic scale. An important area of ongoing research focuses on the role of dark matter in these interactions. Dark matter, which makes up a significant portion of the universe's mass, exerts a gravitational influence but remains invisible to us. Galaxies are thought to reside within halos of dark matter, and these halos play a crucial role during interactions. When galaxies merge, their dark matter halos interact as well, creating gravitational potential wells that influence the distribution of stars and gas. The patterns of tidal tails and bridges can reveal the presence and properties of dark matter, offering indirect evidence of this elusive substance. For instance, simulations of galactic collisions often include models of dark matter to replicate the tidal structures we observe in the universe. These simulations help astronomers understand how galaxies evolve and the role of dark matter in shaping their interactions. By studying the remnants of past mergers and observing ongoing interactions, researchers can refine these models, bringing us closer to understanding the fundamental nature of dark matter. Galactic interactions also play a pivotal role in the large-scale structure of the universe. Over billions of years, galaxies do not merely interact individually but also as part of larger systems, such as galaxy groups and clusters. These structures are themselves subject to gravitational interactions, forming vast cosmic webs of matter. As galaxies and their dark matter halos merge within these larger systems, they contribute to the formation of even more massive structures, such as superclusters. The largest scale of these interactions is reflected in the cosmic web, a vast network of filaments and voids that defines the structure of the universe. Galaxies are not randomly distributed. Instead, they are connected by these filaments of dark matter and gas. Galactic interactions often occur along these filaments, where galaxies are drawn together by their mutual gravitational attraction. The formation of tidal tails and bridges is not limited to isolated galaxies, but is a fundamental process in the shaping of the cosmic web itself. Another fascinating aspect of galactic tides is their impact on the development of supermassive black holes. During galactic mergers, the inflow of gas toward the central regions of galaxies can fuel the growth of these black holes, leading to periods of intense activity. As gas spirals into the black hole, it forms an accretion disk, heating up and emitting immense amounts of energy in the form of radiation. This process can result in the phenomenon of active galactic nuclei (AGN), where the core of a galaxy outshines all its stars combined. The interaction between galaxies can also trigger the formation of quasars, the most luminous type of AGN. Quasars are powered by supermassive black holes consuming large amounts of matter, and their intense energy output can have far-reaching effects on their host galaxies. The radiation from a quasar can heat and expel gas, suppressing further star formation and altering the evolution of the galaxy. Thus, galactic tides not only shape the structure of galaxies but also influence their energetic processes. As galaxies evolve through these interactions, they also create opportunities for the formation of new structures, such as globular clusters and dwarf galaxies. When tidal forces strip material from a galaxy, the resulting stellar streams can coalesce into compact groups of stars. These groups may eventually become globular clusters, orbiting their parent galaxy as relics of its tumultuous past. Similarly, the remnants of tidal debris can give rise to dwarf galaxies, small and faint systems that populate the outskirts of larger galaxies. In this context, the role of tidal forces in redistributing material becomes clear. These forces are not just destructive, they are also creative, enabling the formation of new structures and reshaping galaxies in profound ways. The balance between destruction and creation is a recurring theme in the story of galactic tides, reflecting the dynamic equilibrium that governs the universe. Technological advancements have allowed astronomers to observe these processes with increasing precision. Instruments like the Hubble Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, have provided detailed images of interacting galaxies, revealing the intricate structures formed by tidal forces. These observations not only enhance our understanding of galactic dynamics but also inspire awe at the beauty and complexity of the cosmos. One of the most exciting frontiers in this field is the study of high-redshift galaxies, which are located at great distances and represent the universe in its early stages. Observing interactions between these galaxies offers a glimpse into the processes that shaped the first galaxies and their evolution over cosmic time. These early interactions likely played a crucial role in the formation of the structures we see today, from galaxy clusters to the cosmic web itself. As we look to the future, missions like the James Webb Space Telescope, JWST, promise to revolutionize our understanding of galactic tides and interactions. The JWST's ability to observe in infrared wavelengths will enable it to peer through dust clouds, revealing hidden processes in the hearts of interacting galaxies. This capability will provide unprecedented insights into the role of gas dynamics, star formation, and black hole activity during galactic mergers. The study of galactic tides is not just about understanding the mechanics of gravitational interactions. It is also about exploring our place in the universe. These processes remind us that our galaxy is part of a much larger, interconnected system, where every interaction contributes to the cosmic tapestry. By studying these interactions, we gain a deeper appreciation for the forces that have shaped the universe and continue to influence it today. The story of galactic tides is one of transformation, driven by the relentless pull of gravity and the interplay of matter and energy. From the intricate patterns of tidal tails to the dramatic mergers of galaxies, these interactions reveal the dynamic nature of the cosmos. They remind us that the universe is not static but is constantly evolving, shaped by forces that operate on scales far beyond our comprehension. The ongoing exploration of galactic tides also brings up fascinating questions about the long-term fate of galaxies, including our own Milky Way. Astronomers predict that in about 4.5 billion years, the Milky Way will collide with its neighboring galaxy, Andromeda. This interaction, often referred to as the Milkomeda collision, is expected to result in a dramatic transformation of both galaxies. While this event will not likely cause individual stars to collide, given the vast distances between them, their gravitational interactions will significantly alter the structure and composition of both systems. Simulations of the Milkomeda collision reveal a future filled with tidal tails stretching across the night sky, starburst activity as gas clouds compress, and the eventual coalescence of the two galaxies into a single, larger elliptical galaxy. The supermassive black holes at the centers of the Milky Way and Andromeda will also merge, creating a more massive central black hole surrounded by swirling remnants of both galaxies. This scenario illustrates how galactic interactions drive the evolution of galaxies over cosmic timescales, ultimately shaping their destinies. The concept of galactic cannibalism also ties into the broader theme of galactic evolution. In dense galaxy clusters, larger galaxies often absorb smaller ones, stripping them of their stars and gas through tidal forces. This process, which may seem violent, is a natural consequence of gravity at work. Over time, the larger galaxy grows in size and mass, often forming a diffuse halo of stars around its core. These cannibalized remnants can still be detected as faint stellar streams, providing evidence of past interactions. This process of galactic cannibalism is particularly relevant for understanding the formation of giant elliptical galaxies often found at the centers of clusters. These massive systems are thought to have formed through a series of mergers and accretions, consuming smaller galaxies over billions of years. The central supermassive black holes of these galaxies grow in tandem, fed by the inflowing material from their smaller companions. Studying these systems allows astronomers to reconstruct the history of galaxy clusters and their dominant members. Galactic tides are also deeply connected to the phenomenon of ring galaxies, another intriguing result of gravitational interactions. Ring galaxies form when a smaller galaxy passes through the center of a larger disk galaxy, creating ripples in the larger galaxy's gas and stars. These ripples manifest as concentric rings, often accompanied by regions of intense star formation. Observing ring galaxies offers insights into the mechanics of galactic collisions and the conditions necessary for their creation. Moreover, the phenomenon of polar ring galaxies further underscores the diverse outcomes of galactic interactions. These rare systems feature a ring of gas and stars orbiting at right angles to the main disk of the galaxy. Polar ring galaxies are believed to form through the accretion of material from a companion galaxy, highlighting the intricate interplay of gravity and angular momentum during interactions. The role of tidal forces extends beyond individual galaxies to the larger context of galaxy clusters and superclusters. In these environments, galaxies are subject to the combined gravitational influence of their neighbors and the dark matter halos that envelop the cluster. Tidal forces in clusters can strip galaxies of their gas, a process known as ram pressure stripping, which quenches star formation and alters their evolutionary trajectories. This phenomenon is particularly pronounced in dense clusters like the Virgo cluster, where galaxies exhibit clear signs of tidal interactions. Another captivating aspect of galactic tides is their ability to create stellar streams, long, thin structures composed of stars that have been pulled away from their parent galaxies. Stellar streams often originate from dwarf galaxies or globular clusters disrupted by tidal forces as they orbit a larger galaxy. These streams act as tracers of the gravitational field, providing valuable information about the distribution of dark matter in the host galaxy. For instance, the Sagittarius stream, a prominent stellar stream in the Milky Way, is the remnant of the Sagittarius dwarf galaxy, which has been gradually torn apart by the Milky Way's gravity. By studying the motion and distribution of stars in such streams, astronomers can map the shape and extent of the Milky Way's dark matter halo. This information is critical for understanding the fundamental properties of dark matter and its role in galaxy formation. Galactic tides also influence the fate of satellite galaxies orbiting larger systems. Over time, tidal forces can strip these satellites of their stars, gas, and dark matter, leaving behind faint remnants known as ultra-faint dwarf galaxies. These objects are among the smallest and oldest known galaxies, offering a unique window into the early universe. Their survival and disruption provide clues about the strength and distribution of tidal forces within the host galaxy. The interplay of galactic tides with magnetic fields adds another layer of complexity to these interactions. When galaxies collide or merge, their magnetic fields can become tangled and amplified, influencing the behavior of charged particles and the dynamics of interstellar gas. These magnetic interactions can affect the formation of stars and the distribution of cosmic rays, adding to the multifaceted nature of galactic evolution. As we delve deeper into the mysteries of galactic tides, the advent of next-generation telescopes and instruments promises to unveil even more details about these processes. Projects like the Vera C. Rubin Observatory, with its ability to conduct wide-field surveys, will enable astronomers to detect faint tidal features around galaxies, revealing evidence of past interactions. Similarly, the Square Kilometre Array, SKA, will provide unprecedented sensitivity to radio emissions, allowing researchers to study the gas dynamics in interacting galaxies. The study of galactic tides is not merely an academic pursuit, it has profound implications for our understanding of the universe. These interactions remind us of the interconnectedness of cosmic structures and the dynamic processes that shape them. They challenge us to think beyond static snapshots of galaxies and embrace a more fluid, ever-changing view of the cosmos. In this dance of galaxies, we find echoes of the broader forces that govern the universe: gravity, dark matter, and the relentless drive toward equilibrium. By studying galactic tides, we gain a deeper appreciation for the complexity and beauty of the universe, as well as our own place within it. Every tidal tale, every stellar stream, and every merging galaxy tells a story of connection and transformation, a story that continues to unfold across the vast expanse of space. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.